Hello everyone, and welcome back. We are making some terrific progress. Let's see how far we've come. We've got a data set, we've prepared our data loaders, we've built a baseline model, and we've trained it, evaluated it. Now it's time, and the last video, we set up device agnostic code. But where are we in our little framework? We're up to improving through experimentation. And quite often that is building a different model and trying it out. It could be using more data. It could be tweaking a whole bunch of different things. And so let's get into some coding. I'm going to write it here. Model 1. I believe we're up to section 6 now. Model 1 is going to be building a better model with nonlinearity. So I issued you the challenge in the last video to give it a go to try and build a model with nonlinearity. I hope you gave it a go, because if anything that this course, I'm trying to impart on you in this course, it's to give things a go, to try things out, because that's what machine learning and coding is all about. Trying things out, giving it a go. But let's write down here. We learned about the power of nonlinearity in notebook 02. So if we go to the Learn PyTorch.io book, we go to section number 2. We'll just wait for this to load. And then if we come down here, we can search for nonlinearity. The missing piece, nonlinearity. So I'm going to get this and just copy that in there. If you want to see what nonlinearity helps us do, it helps us model non-linear data. And in the case of a circle, can we model that with straight lines? In other words, linear lines. Recall, linear means straight, non-linear means non-straight. And so we learned that through the power of linear and non-linear functions, neural networks can model almost any kind of data if we pair them in the right way. So you can go back through and read that there, but I prefer to code things out and try it out on our data. So let's create a model with non-linear and linear layers. But we also saw that our model with just linear layers can model our data. It's performing quite well. So that's where the experimentation side of things will come into play. Sometimes you won't know what a model will do, whether it will work or won't work on your data set, but that is where we try different things out. So we come up here, we look at our data. That looks actually quite linear to me as a bag. Like it's just some straight lines. You could maybe model that with just straight lines. But there are some things which you could potentially classify as nonlinear in here. It's hard to tell without knowing. So let's give it a go. Let's write a nonlinear model, which is going to be quite similar to model 0 here, except we're going to intersperse some ReLU layers in between our linear layers. So recall that ReLU is a nonlinear activation function, and ReLU has the formula, if something comes in and it's a negative value, ReLU is going to turn that negative into a 0, and if something is positive, ReLU is just going to leave it there. So let's create another class here, fashion MNIST model v1, and we're going to subclass from nn.module. Beautiful. And then we're going to initialize our model. This is going to be quite the same as what we created before. We want an input shape, and that's going to be an integer. And then we want a number of hidden units, and that's going to be an int here. And then we want an output shape, int. And I want to stress as well that although we're creating a class here with these inputs, classes are as flexible as functions. So if you need different use cases for your modeling classes, just keep that in mind that you can build that functionality in. Self.layerStack. We're going to spell layerStack correctly. And we're going to set this equal to nn.sequential because we just want a sequential set of layers. The first one's going to be nn.flatten, which is going to be flatten inputs into a single vector. And then we're going to go nn.linear because we want to flatten our stuff because we want it to be the right shape. If we don't flatten it, we get shape issues. Input shape. And then the out features of our linear layer is going to be the hidden units. Hidden units. I'm just going to make some code cells here so that my code goes into the middle of the screen. Then here is where we're going to add a nonlinear layer. So this is where we're going to add in a ReLU function. And where might we put these? Well, generally you'll have a linear function followed by a nonlinear function in the construction of neural networks. However, Neural networks are as customizable as you can imagine. Whether they work or not is a different question. So we'll go output shape here as the out features. Oh, do we mess this one up? Yes, we did. This needs to be hidden units. And why is that? Well, it's because the output shape of this linear layer here needs to match up with the input shape of this linear layer here. The ReLU layer won't change the shape of our data. And you could test that out by printing the different shapes if you'd like. And then we're going to finish off with another nonlinear layer at the end. ReLU. Now, do you think that this will improve our model's results or not? Well, it's hard to tell without trying it out, right? So let's continue building our model. We have to override the forward method. Self x is going to be, we'll give a type hint here. This is going to be a torch tensor as the input. And then we're just going to return what's happening here. We'll go self.layer stack x. So that just means that x is going to pass through our layer stack here. And we could customize this. We could try it just with one nonlinear activation. This is actually our previous network, just with those commented out. All we've done is added in 2 ReLU functions. And so I'm going to run that. Beautiful. And so what should we do next? Well, we should instantiate it, but previously we ran our last model, model 0, on, if we go parameters, do we run this on the GPU or the CPU? On the CPU. So how about we try out our Fashion MNIST model V1 running on the device that we just set up, which should be CUDA. Wonderful. So we can instantiate. So create an instance of model 1. So we want model 1, or actually, we'll set up a manual seed here so that whenever we create a new instance of a model, it's going to be instantiated with random numbers. We don't necessarily have to set a random seed, but we do so anyway so that our values are quite similar on your end and my end. Input shape is going to be 784. Where does that come from? Well, that's because this is the output of the flatten layer after our 28 by 28 image goes in. Then we're going to set up the hidden units. We're going to use the same number of hidden units as before, which is going to be 10. And then the output shape is what? We need one value, one output neuron for each of our classes. So length of the class names. And then we're going to send this to the target device. So we can write send to the GPU if it's available. So now that we've set up device agnostic code in the last video, we can just put to device instead of hard coding that. And so if we check, so this was the output for model 0's device. Let's now check model 1's device. Model 1, parameters, and we can check where those parameters live by using the device attribute. Beautiful. So our model 1 is now living on the GPU, CUDA, at index 0. Index 0 means that it's on the first GPU that we have available. We only have one GPU available, so it's on this Tesla T4 GPU. Now, we've got a couple more things to do. Now that we've created another model, we can recreate, if we go back to our workflow, we've just built a model here. What do we have to do after we built a model? We have to instantiate a loss function and an optimizer. Now, we've done both of those things for model 0, so that's what we're going to do in the next video, but I'd like you to go ahead and try to create a loss function for our model and an optimizer for model 1. The hint is that they can be the exact same loss function and optimizer as model 0. So give that a shot, and I'll see you in the next video. Welcome back. In the last video, we created another model. So we're continuing with our modeling experiments. And the only difference here between Fashion MNIST model V1 and V0 is that we've added in nonlinear layers. Now, we don't know for now. We could think or guess whether they would help improve our model. And with practice, you can start to understand how different functions will influence your neural networks. But I prefer to, if in doubt, code it out, run lots of different experiments. So let's continue. We now have to create a loss function, loss, optimizer, and evaluation metrics. So we've done this for model 0. So we're not going to spend too much time explaining what's going on here. And we've done this a fair few times now. So from helper functions, which is the script we downloaded before, we're going to import our accuracy function. and we're going to set up a loss function, which is, we're working with multi-class classification. So what loss function do we typically use? nn.cross entropy loss. And as our optimizer is going to be torch.optim.sgd. And we're going to optimize this time, I'll put in the params keyword here, model1.parameters. And the learning rate, we're just going to keep it the same as our previous model. And that's a thing to keep a note for your experiments. When you're running fair few experiments, you only really want to tweak a couple of things, or maybe just one thing per experiment. That way you can really narrow down what actually influences your model and what improves it / what doesn't improve it. And a little pop quiz, what does the loss function do? This is going to measure how wrong our model is. And what does the optimizer do? Tries to update our model's parameters to reduce the loss. So that's what these two functions are going to be doing. The accuracy function is, of course, going to be measuring our model's accuracy. We measure the accuracy because that's one of the base classification metrics. So we'll run this. Now what's next? We're getting quite good at this. We've picked a loss function and an optimizer. Now we're going to build a training loop. However, we spent quite a bit of time doing that in a previous video. If we go up here, that was our eval model function. Oh, that was helpful. We turned it into a function. How about we do the same with these? Why don't we make a function for our training loop as well as our testing loop? So I think you can give this a go. We're going to make a function in the next video for training. We're going to call that train step. And we'll create a function for testing called test step. Now they'll both have to take in some parameters. I'll let you figure out what they are, but otherwise we're going to code that up together in the next video. So I'll see you there. So we've got a loss function ready and an optimizer. What's our next step? Well, it's to create training and evaluation loops. So let's make a heading here. We're going to call this functionizing training and evaluation or / testing loops, because we've written similar code quite often for training and evaluating / testing our models. Now, we're going to start moving towards functionizing code that we've written before, because that's not only a best practice, it helps reduce errors, because if you're writing a training loop all the time, we may get it wrong. If we've got one that works for our particular problem, hey, we might as well save that as a function so we can continually call that over and over and over again. So how about we, and this is going to be very rare that I'm going to allow you to do this, is we're going to copy this training, and you might have already attempted to create this. That is a function called, let's create a function for one training loop, and we're going to call this train step. And we're going to create a function for the testing loop. We're going to call this test step. Now, these are just what I'm calling them. You can call them whatever you want. I just understand it quite easily by calling it train step. And then we can, for each epoch in a range, we call our training step. And then the same thing for each epoch in a range, we can call a testing step. This will make a lot more sense once we've coded it out. So let's put the training code here. To functionize this, let's start it off with train step. Now, what parameters should our train step function take in? Well, let's think about this. We need a model, we need a data loader, we need a loss function, and we need an optimizer. We could also put in an accuracy function here if we wanted to, and potentially, it's not here, but we could put in what target device we'd like to compute on and make our code device agnostic. So this is just the exact same code we went through before. We loop through a data loader, we do the forward pass, we calculate the loss, we accumulate it, we zero the optimizer, we perform backpropagation in respect to the loss with the parameters of the model, and then we step the optimizer to hopefully improve the parameters of our model to better predict the data that we're trying to predict. So let's craft a train step function here. We'll take a model, which is going to be torch nn.module, type hint, And we're going to put in a data loader, which is going to be of type torch utils.data.data loader. Now we don't necessarily need to put this in, these type hints, but they're a relatively new addition to Python. And so you might start to see them more and more. And it also just helps people understand what your code is expecting. So the loss function, we're going to put in an optimizer, torch.optim, which is a type optimizer. We also want an accuracy function. We don't necessarily need this either. These are a lot of nice to haves. The first four are probably the most important, and then the device. So torch, this is going to be torch.device equals device. So we'll just hard code that to be our already set device parameter. And we'll just write in here, performs training step with model trying to learn on data loader. Nice and simple. We could make that more explanatory if we wanted to, but we'll leave it at that for now. And so, right at the start, we're going to set up train loss and train ac equals 0, 0. We're going to introduce accuracy here. So we can get rid of this. Let's just go through this line by line. What do we need to do here? Well, we've got for batch xy in enumerate train data loader, but we're going to change that to data loader up here. So we can just change this to data loader. Wonderful. And now we've got model 0.train. Do we want that? Well, no, because we're going to keep this model agnostic. We want to be able to use any model with this function. So let's get rid of this, model.train. We are missing one step here, is put data on target device. And we could actually put this model.train up here. Put model into training mode. Now this will be the default for the model, but just in case, we're going to call it anyway. Model.train. Put data on the target device. So we're going to go x, y equals x.to device, y.to device. Wonderful. And the forward pass, we don't need to use model 0 anymore. We're just going to use model that's up here. The loss function can stay the same because we're passing in a loss function up there. The train loss can be accumulated, that's fine. But we might also accumulate now the train accuracy. Calculate loss and accuracy per batch. So train ac equals or plus equals our accuracy function on y true equals y and y pred equals y pred. So the outputs here, y pred, we need to take, because the raw outputs the raw logits from the model, because our accuracy function expects our predictions to be in the same format as our true values, we need to make sure that they are. We can call the argmax here on the first dimension. This is going to go from logits to prediction labels. We can keep the optimizer 0 grad the same because we're passing in an optimizer up here. We can keep the loss backwards because the loss is just calculated there. We can keep optimizer step, and we could print out what's happening, but we might change this up a little bit. We need to divide the total train loss and accuracy. I just want to type in accuracy here because now we've added in the accuracy metric. Ac. So train ac divided equals length train data loader. Oh no, sorry. We can just use the data loader here. Data loader. Data loader. And we're not going to print out per batch here. I'm just going to get rid of this. We'll make, at the end of this step, we will make our printout here. Print. Notice how it's at the end of the step because we're outside the for loop now. So we're going to, here we're accumulating the loss on the training data set and the accuracy on the training data set per batch. And then we're finding out at the end of the training step, so after it's been through all the batches in the data loader, we're finding out what the average loss is per batch and the average accuracy is per batch. And now we're going to go train loss is going to be the train loss on 0.5. And then we're going to go train ac is going to be train ac. And we're going to set that to 0.2f. We'll get that there. Percentage. Wonderful. So if all this works, we should be able to call our train step function and pass it in a model, a data loader, a loss function, an optimizer, an accuracy function, and a device. And it should automatically do all of these steps. So we're going to find that out in a later video. In the next video, we're going to do the same thing we've just done for the training loop with the test step. But here's your challenge for this video, is to go up to the testing loop code we wrote before and try to recreate the test step function in the same format that we've done here. So give that a go, and I'll see you in the next video. Welcome back. In the last video, we functionalized our training loop. So now we can call this train step function, and instead of writing all this training loop code again, well, we can train our model through the art of a function. Now, let's do the same for our testing loop. So I issued you the challenge in the last video to give it a go. I hope you did, because that's the best way to practice PyTorch code, is to write more PyTorch code. Let's put in a model, which is going to be torch nn.module. And we're going to put in a data loader, because we need a model and we need data. The data loader is going to be, of course, the test data loader here, torch.utils.data.data loader. And then we're going to put in a loss function, which is going to be torch nn.module as well, because we're going to use nn.cross-entropy loss. We'll see that later on. We're going to put in an accuracy function. We don't need an optimizer because we're not doing any optimization in the testing loop. We're just evaluating. And the device can be torch.device, and we're going to set that as a default to the target device parameter. Beautiful. So we'll put a little doc string here. So performs a testing loop step on model going over data loader. Wonderful. So now let's set up a test loss and a test accuracy, because we'll measure test loss and accuracy with our testing loop function. And we're going to set the model into, I'll just put a comment here. Put the model in eval mode. So model.eval. We don't have to use any underscore here, as in model 0, because we have a model coming in the top here. Now, what should we do? Well, because we're performing a test step, we should turn on inference mode. So turn on inference mode context manager. Remember, whenever you're performing predictions with your model, you should put it in model.eval, and if you want as many speed ups as you can get, make sure the predictions are done within the inference mode, because remember, inference is another word for predictions, within the inference mode context manager. So we're going to loop through our data loader for x and y in data loader. We don't have to specify that this is x test or y test. We could if we wanted to, but because we're in another function here, we can just go for x, y in data loader. We can do the forward pass after we send the data to the target device. So we're going to have x, y equals x.to device. And the same thing with y. We're just doing best practice here, creating device agnostic code. Then what should we do? Well, we should do the thing that I said before, which is the forward pass. Now that our data and model will be on the same device, we can create a variable here, test pred equals model. We're going to pass in x. And then what do? We can calculate the loss. So to calculate the loss / accuracy, we're going to accumulate it per batch. So we'll set up test loss equals loss function, plus equals loss function. We're going to pass it in test pred and y, which is our truth label, and then the test acc, where you will accumulate as well. Using our accuracy function, we'll pass in y true equals y, and then y pred. What do we have to do to y pred? Well, our test pred, we have to take the argmax to convert it from, so this is going to outputs raw logits. Remember, a model's raw output is referred to as logits. And then here, we have to go from logits to prediction labels. Beautiful. Oh, little typo here. Did you catch that one? Tab. Beautiful. Oh, look how good this function is looking. Now we're going to adjust the metrics. So adjust metrics and print out. You might notice that we're outside of the batch loop here, right? So if we draw down from this line 4 and we write some code here, we're still within the context manager. This is important because if we want to adapt a value created inside the context manager, we have to modify it still within inside that context manager. Otherwise, PyTorch will throw an error. So try to write this code if you want outside the context manager and see if it still works. So test loss, we're going to adjust it to find out the average test loss and test accuracy per batch across a whole step. So we're going to go length data loader. Then we're going to print out what's happening. Print out what's happening. So test loss. What should we put in here? Well, we're going to get the test loss. Let's get this to 5 decimal places. And then we're going to go test acc, and we will get that to 2 decimal places. You could do this as many decimals as you want. You could even times it by 100 to get it in proper accuracy format. And we'll put a new line on the end here. Wonderful. So now it looks like we've got functions, I haven't run this cell yet, for a training step and a test step. So how do you think we could replicate, if we go back up to our training loop that we wrote before, how do you think we could replicate the functionality of this, except this time using our functions? Well, we could still use this for epoch in TQDM range epochs, but then we would just call our training step for this training code, our training step function, and we would call our testing step function, passing in the appropriate parameters for our testing loop. So that's what we'll do in the next video. We will leverage our 2 functions, train step and test step, to train model 1. But here's your challenge for this video. Give that a go. So use our training step and test step function to train model 1 for 3 epochs and see how you go. But we'll do it together in the next video. Welcome back. How'd you go? Did you create a training loop or a PyTorch optimization loop using our training step function and a test step function? Were there any errors? In fact, I don't even know. But how about we find out together, hey? How do we combine these 2 functions to create an optimization loop? So I'm going to go torch.manualseed 42, and I'm going to measure the time of how long our training and test loop takes. This time we're using a different model. So this model uses nonlinearities and it's on the GPU. So that's the main thing we want to compare, is how long our model took on CPU versus GPU. So I'm going to import from timeIt, import default timer as timer. And I'm going to start the train time. Train time start on GPU equals timer. And then I'll just write here, set epochs. I'm going to set epochs equal to 3 because we want to keep our training experiments as close to the same as possible so we can see what little changes do what. And then it's create a optimization and evaluation loop using train step and test step. So we're going to loop through the epochs for epoch in TQDM. So we get a nice progress bar in epochs. Then we're going to print epoch, little printout of what's going on, epoch, and we'll get a new line, and then maybe 1, 2, 3, 4, 5, 6, 7, 8 or something like that. Maybe I miscounted there, but that's all right. Train step, what do we have to do for this? Now we have a little doc string, we have a model. What model would we like to use? We'd like to use model 1. We have a data loader. What data loader would we like to use? Well, we'd like to use our train data loader. We also have a loss function, which is our loss function. We have an optimizer, which is our optimizer. And we have an accuracy function, which is our accuracy function. And oops, forgot to put fn. And finally, we have a device, which equals device, but we're going to set that anyway. So how beautiful is that for creating a training loop? Thanks to the code that we've functionized before. And just recall, we set our optimizer and loss function in a previous video. You could bring these down here if you really wanted to, so that they're all in one place. Either way up, but we can just get rid of that because we've already set it. Now, we're going to do the same thing for our test step. So what do we need here? Let's check the doc string. We could put a little bit more information in this doc string if we wanted to really make our code more reusable, and so that if someone else was to use our code, or even us in the future, knows what's going on. But let's just code it out because it's still fresh in our minds. Model equals model1. What's our data loader going to be for the test step? It's going to be our test data loader. Then we're going to set in a loss function, which is going to be just the same loss function. We don't need to use an optimizer here because we are only evaluating our model, but we can pass in our accuracy function. And then finally, the device is already set, but we can just pass it in anyway. Look at that. Our whole optimization loop in a few lines of code. Isn't that beautiful? So these functions are something that you could put in, like our helper functions.py. And that way you could just import it later on and you don't have to write your training loops all over again. But we'll see more of an example of that later on in the course. So let's keep going. We want to measure the train time, right? So we're going to create, once it's been through these steps, we're going to create train time end on CPU. And then we're going to set that to the timer. So all this is going to do is measure a value in time. Once this line of code is run, it's going to run all of these lines of code. So it's going to perform the training and optimization loop. And then it's going to, this should be GPU. It's going to measure a point in time here. So once all this code's run, measure a point in time there. And then finally, we can go total train time for model 1 is equal to print train time, which is our function that we wrote before. And we pass it in a start time, and it prints the difference between the start and end time on a target device. So let's do that. Start equals what? Train time start on GPU. The end is going to be train time end on GPU. And the device is going to be device. Beautiful. So are you ready to run our next modeling experiment, model 1? We've got a model running on the GPU and it's using nonlinear layers, and we want to compare it to our first model, which our results were model 0 results. And we have total train time on model 0. Yes, we do. So this is what we're going for. Does our model 1 beat these results, and does it beat this result here? So 3, 2, 1. Do we have any errors? No, we don't. Okay. Train step got an unexpected keyword loss. Oh, did you catch that? I didn't type in loss function. Let's run it again. There we go. Okay, we're running. We've got a progress bar. It's going to output at the end of each epoch. There we go. Training loss. All right. Test accuracy, training accuracy. This is so exciting. I love watching neural networks train. Okay, we're improving per epoch. That's a good sign. But we've still got a fair way to go. Oh, okay. So what do we have here? Well, we didn't beat our... it looks like we didn't beat our model 0 results with the nonlinear layers. And we only just slightly had a faster training time. Now again, your numbers might not be the exact same as what I've got here, right? So that's a big thing about machine learning, is that it uses randomness, so your numbers might be slightly different. The direction should be quite similar, and we may be using different GPUs. So just keep that in mind. Right now, I'm using a NVIDIA SMI. I'm using a Tesla T4, which is, at the time of recording this video, Wednesday, April 20, 2022, is a relatively fast GPU for making inference. So just keep that in mind. Your GPU in the future may be different, and your CPU that you run may also have a different time here. So if these numbers are like 10 times higher, you might want to look into seeing if your code there's some error. If they're 10 times lower, well, hey, you're running it on some fast hardware. So it looks like my code is running on CUDA slightly faster than the CPU, but not dramatically faster. And that's probably akin to the fact that our dataset isn't too complex and our model isn't too large. What I mean by that is our model doesn't have like a vast amount of layers, and our data set is only comprised of, like, this is the layers our model has. And our data set is only comprised of 60,000 images that are 28 by 28. So as you can imagine, the more parameters in your model, the more features in your data, the higher this time is going to be. And you might sometimes even find that your model is faster on CPU. So this is the train time on CPU. You might sometimes find that your model's training time on a CPU is, in fact, faster for the exact same code running on a GPU. Now, why might that be? Well, let's write down this here. Let's go note. Sometimes, depending on your data/hardware, you might find that your model trains faster on CPU than GPU. Now, why is this? So one of the number one reasons is that, one, it could be that the overhead for copying data/model to and from the GPU outweighs the compute benefits offered by the GPU. So that's probably one of the number one reasons, is that you have to, for data to be processed on a GPU, you have to copy it because it is by default on the CPU. If you have to copy it to that GPU, you have some overhead time for doing that copy into the GPU memory. And then although the GPU will probably compute faster on that data once it's there, you still have that back and forth of going between the CPU and the GPU. And the number two reason is that the hardware you're using has a better CPU in terms of compute capability than the GPU. Now, this is quite a bit rarer. Usually, if you're using a GPU, like a fairly modern GPU, it will be faster at computing deep learning or running deep learning algorithms than your general CPU. But sometimes these numbers of compute time are really dependent on the hardware that you're running. So you'll get the biggest benefits of speed ups on the GPU when you're running larger models, larger data sets, and more compute intensive layers in your neural networks. And so if you'd like a great article on how to get the most out of your GPUs, it's a little bit technical, but this is something to keep in mind as you progress as a machine learning engineer, is how to make your GPUs go brr, and I mean that, brr, from first principles. There we go. Making deep learning go brr, as in your GPU is going brr because it's running so fast, from first principles. So this is by Horace Heh, who works on PyTorch, and it's great. It talks about compute as a first principle. So here's what I mean by copying memory and compute. There might be a fair few things you're not familiar with here, but that's okay. But just be aware, bandwidth. So bandwidth costs are essentially the cost paid to move data from one place to another. That's what I was talking about, copying stuff from the CPU to the GPU. And then also there's one more. Where is it? Overhead. Overhead is basically everything else. I called it overhead. There are different terms for different things. This article is excellent. So I'm going to just copy this in here, and you'll find this in the resources, by the way. So for more on how to make your models compute faster, see here. Lovely. So right now, our baseline model is performing the best in terms of results and in terms of, or actually, our model computing on the GPU is performing faster than our CPU. Again, yours might be slightly different. For my case, for my particular hardware, CUDA is faster, except Model 0, our baseline, is better than Model 1. So what's to do next? Well, it's to keep experimenting, of course. I'll see you in the next video. Welcome back. Now, before we move on to the next modeling experiment, let's get a results dictionary for our Model 1, our model that we trained on. So just like we've got one for Model 0, let's create one of these for Model 1 results, and we can create that with our eval model function. So we'll go right back down to where we were. I'll just get rid of this cell, and let's type in here, get Model 1 results dictionary. This is helpful so later on we can compare all of our modeling results because they'll all be in dictionary format. So we'll go Model 1 results equals eval model on our model equals model1, and we can pass in a data loader, which is going to be our test data loader. Then we can pass in a loss function, which is going to equal our loss function, and we can pass in our accuracy function, equals accuracy function. Wonderful, and then if we check out our model 1 results, what do we get? Oh no, we get an error. Do we get the code right? That looks right to me. Oh, what does this say? Runtime error. Expected all tensors to be on the same device, but found at least 2 devices, CUDA and CPU. Of course. So why did this happen? Well, let's go back up to our eval model function, wherever we defined that. Here we go. Ah, I see. So this is a little gotcha in PyTorch or in deep learning in general. There's a saying in the industry that deep learning models fail silently, and this is kind of one of those ones. It's because our data and our model are on different devices. So remember how I said the 3 big errors are shape mismatches with your data and your model, device mismatches, which is what we've got so far, and then data type mismatches, which is if your data is in the wrong data type to be computed on. So what we're going to have to do to fix this is, let's bring down our eval model function down to where we were. And just like we've done in our test step and train step functions, where we've created device agnostic data here, we've sent our data to the target device, we'll do that exact same thing in our eval model function. And this is just a note for going forward. It's always handy to, where you can, create device agnostic code. So we've got our new eval model function here for XY in our data loader. Let's make our data device agnostic. So just like our model is device agnostic, we've sent it to the target device, we will do the same here. X.toDevice and then Y.toDevice. Let's see if that works. We will just rerun this cell up here. I'll grab this. We're just going to write the exact same code as what we did before, but now it should work because we've sent our... We could actually also just pass in the target device here. Device equals device. That way we can pass in whatever device we want to run it on. And we're going to just add in device here. Device equals device. And let's see if this runs correctly. Beautiful. So if we compare this to our model 0 results, it looks like our baseline's still out in front. But that's okay. We're going to, in the next video, start to step things up a notch and move on to convolutional neural networks. This is very exciting. And by the way, just remember, if your numbers here aren't exactly the same as mine, don't worry too much. If they're outlandishly different, just go back through your code and see if it's maybe a cell hasn't been run correctly or something like that. If there are a few decimal places off, that's okay. That's due to the inherent randomness of machine learning and deep learning. But with that being said, I'll see you in the next video. Let's get our hands on convolutional neural networks. Welcome back. In the last video, we saw that our second modeling experiment, model 1, didn't quite beat our baseline. But now we're going to keep going with modeling experiments, and we're going to move on to model 2, and this is very exciting. We're going to build a convolutional neural network, which are also known as CNN. CNNs are also known as convnets, and CNNs are known for their capabilities to find patterns in visual data. So, what are we going to do? Well, let's jump back into the keynote. We had a look at this slide before, where this is the typical architecture of a CNN. And there's a fair bit going on here, but we're going to step through it one by one. We have an input layer, just like any other deep learning model. We have to input some kind of data. We have a bunch of hidden layers. In our case, in a convolutional neural network, you have convolutional layers. You often have hidden activations or nonlinear activation layers. You might have a pooling layer. You generally always have an output layer of some sort, which is usually a linear layer. And so the values for each of these different layers will depend on the problem you're working on. So we're going to work towards building something like this. And you'll notice that a lot of the code is quite similar to the code that we've been writing before for other PyTorch models. The only difference is in here is that we're going to use different layer types. And so if we want to visualize a CNN in a colored block edition, we're going to code this out in a minute, so don't worry too much. We have a simple CNN. You might have an input, which could be this image of my dad eating some pizza with 2 thumbs up. We're going to pre-process that input. We're going to, in other words, turn it into a tensor in red, green, and blue for an image. And then we're going to pass it through a combination of convolutional layers, ReLU layers, and pooling layers. Now, again, this is a thing to note about deep learning models. I don't want you to get too bogged down in the order of how these layers go, because they can be combined in many different ways. In fact, research is coming out almost every day, every week, about how to best construct these layers. The overall principle is what's more important, is how do you get your inputs into an idealized output? And that's the fun part. And then, of course, we have the linear output layer, which is going to output however many classes or value for however many classes that we have in the case of classification. And then if you want to make your CNN deeper, this is where the deep comes from deep learning. You can add more layers. So the theory behind this, or the practice behind this, is that the more layers you add to your deep learning model, the more chances it has to find patterns in the data. Now, how does it find these patterns? Well, each one of these layers here is going to perform, just like what we've seen before, a different combination of mathematical operations on whatever data we feed it. And each subsequent layer receives its input from the previous layer. In this case, there are some advanced networks that you'll probably come across later in your research and machine learning career that use inputs from layers that are kind of over here all the way down here or something like that. They're known as residual connections, but that's beyond the scope of what we're covering for now. We just want to build our first convolutional neural network. And so let's go back to Google Chrome. I'm going to show you my favorite website to learn about convolutional neural networks. It is the CNN Explainer website. And this is going to be part of your extra curriculum for this video, is to spend 20 minutes clicking and going through this entire website. We're not going to do that together because I would like you to explore it yourself. That is the best way to learn. So what you'll notice up here is we have some images of some different sort, and this is going to be our input. So let's start with pizza. And then we have a convolutional layer, a ReLU layer, a conv layer, a ReLU layer, a max pool layer, conv2, ReLU2, conv2, ReLU2, max pool 2. This architecture is a convolutional neural network, and it's running live in the browser. And so we pass this image, you'll notice that it breaks down into red, green, and blue. And then it goes through each of these layers and something happens. And then finally we have an output. And you'll notice that the output has 10 different classes here because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different classes of image in this demo here. And of course, we could change this. If we had 100 classes, we might change this to 100. But the pieces of the puzzle here would still stay quite the same. And you'll notice that the class pizza has the highest output value here because our image is of pizza. If we change to, what is this one? Espresso. It's got the highest value there. So this is a pretty well-performing convolutional neural network. Then we have a sport car. Now, if we clicked on each one of these, something is going to happen. Let's find out. We have a convolutional layer. So we have an input of an image here that's 64 by 3. This is Color Channel's last format. So we have a kernel, and this kernel, this is what happens inside a convolutional layer. And you might be going, well, there's a lot going on here. And yes, of course there is, if this is the first time you've ever seen this. But essentially what's happening is a kernel, which is also known as a filter, is going over our image pixel values, because of course they will be in the format of a tensor, and trying to find small little intricate patterns in that data. So if we have a look at here, and this is why it's so valuable to go through this and just play around with it. We start in the top left corner and then slowly move along. You'll see on the output on the right-hand side, we have another little square. And do you notice in the middle all of those numbers changing? Well, that is the mathematical operation that's happening as a convolutional layer convolves over our input image. How cool is that? And you might be able to see on the output there that there's some slight values for, like, look around the headlight here. Do you notice on the right how there's some activation? There's some red tiles there. Well, that just means that potentially this layer or this hidden unit and I want to zoom out for a second, is we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hidden units. Each one of these is going to learn a different feature about the data. And now the beauty of deep learning, but also one of the curses of deep learning, is that we don't actually control what each one of these learns. The magic of deep learning is that it figures it out itself what is best to learn. If we go into here, notice that each one we click on has a different representation on the right-hand side. And so this is what's going to happen layer by layer as it goes through the convolutional neural network. And so if you want to read about what is a convolutional neural network, you can go through here. But we're going to replicate this exact neural network here with PyTorch code. That's how I'd prefer to learn it. But if you want the intuition behind it, the math behind it, you can check out all of these resources here. That is your extra curriculum for this video. So we have an input layer, we have a convolutional layer. You can see how the input gets modified by some sort of mathematical operation, which is of course the convolutional operation. And we have there all different numbers, finding different patterns in data. This is a really good example here. You notice that the output size slightly changes. That'll be a trend throughout each layer. And then we can understand the different hyperparameters, but I'm going to leave this for you to explore on your own. In the next video, we're going to start to write PyTorch code to replicate everything that's going on here. So I'm going to link this in here to find out what's happening inside CNN. See this website here. So join me in the next video. This is super exciting. We're going to build our first convolutional neural network for computer vision. I'll see you there. Welcome back. In the last video, we went briefly through the CNN Explainer website, which is my favorite resource for learning about convolutional neural networks. And of course, we could spend 20 minutes clicking through everything here to find out what's going on with a convolutional neural network. Or we could start to code one up. So how about we do that, hey? If in doubt, code it out. So we're going to create a convolutional neural network. And what I'm going to do is I'm going to build this, or we're going to build this model together in this video. And then because it's going to use layers or PyTorch layers that we haven't looked at before, we're going to spend the next couple of videos stepping through those layers. So just bear with me as we code this entire model together. We'll go break it down in subsequent videos. So let's build our first convolutional neural network. That's a mouthful, by the way. I'm just going to probably stick to saying CNN. Fashion MNIST. We're up to model v2. We're going to subclass nn.module, as we always do when we're building a PyTorch model. And in here, we're going to say model architecture that replicates the tiny VGG. And you might be thinking, where did you get that from, Daniel? Model from CNN Explainer website. And so oftentimes when convolutional neural networks or new types of architecture come out, the authors of the research paper that present the model get to name the model. And so that way in the future, you can refer to different types of model architectures with just a simple name like tiny VGG, and people kind of know what's going on. So I believe somewhere on here it's called tiny VGG. Tiny VGG. We have nothing. Yeah, there we go. In tiny VGG. And do we have more than one tiny? Tiny, yeah. Tiny VGG. And if we look up VGG, ConvNet, VGG 16 was one of the original ones. VGG, Very Deep Convolutional Neural Networks, VGGNet. There's also ResNet, which is another convolutional neural network. You can also, I don't want to give you my location, Google. You can go popular CNN architectures. And this will give you a fair few options. LaNet is one of the first, AlexNet, ZFNet, whole bunch of different resources. And also, how could you find out more about a convolutional neural network? What is a convolutional neural network? You could go through that. But let's stop that for a moment. Let's code this one up together. So we're going to initialize our class here, def init. We're going to pass it in an input shape, just like we often do. We're going to put in a number of hidden units, which is an int. And we're going to put in an output shape, which is an int. Wonderful. So nothing too outlandish that we haven't seen before there. And we're going to go super.init to initialize our initializer, for lack of a better way of putting it. Now, we're going to create our neural network in a couple of blocks this time. And you might often hear when you learn more about convolutional neural networks, or I'll just tell you that things are often referred to as convolutional blocks. So if we go back to our keynote, this combination of layers might be referred to as a convolutional block. And a convolutional block, a deeper CNN, might be comprised of multiple convolutional blocks. So to add to the confusion, a block is comprised of multiple layers, and then an overall architecture is comprised of multiple blocks. And so the deeper and deeper your models get, the more blocks it might be comprised of, and the more layers those blocks may be comprised of within them. So it's kind of like Lego, which is very fun. So let's put together an NN sequential. Now, the first few layers here that we're going to create in conv block 1 are nn.conv2d. Oh, look at that. Us writing our first CNN layer. And we have to define something here which is in channels. So this channels refers to the number of channels in your visual data. And we're going to put in input shape. So we're defining the input shape. This is going to be the first layer in our model. The input shape is going to be what we define when we instantiate this class. And then the out channels. Oh, what's the out channels going to be? Well, it's going to be hidden units, just like we've done with our previous models. Now, the difference here is that in nn-conv2d, we have a number of different hyperparameters that we can set. I'm going to set some pretty quickly here, but then we're going to step back through them, not only in this video, but in subsequent videos. Oh, we've got a fair bit going on here. We've got in channels, which is our input shape. We've got out channels, which are our hidden units. We've got a kernel size, which equals 3, or this could be a tuple as well, 3 by 3, but I just like to keep it as 3. We've got a stride and we've got padding. Now, because these are values we can set ourselves, what are they referred to as? Let's write this down. Values we can set ourselves in our neural networks, in our NNs, neural networks, are called hyperparameters. So these are the hyperparameters of nn-conv2d. And you might be thinking, what is 2D for? Well, because we're working with two-dimensional data, our images have height and width. There's also conv1d for one-dimensional data, 3D for three-dimensional data. We're going to stick with 2D for now. And so what do each of these hyperparameters do? Well, before we go through what each one of them do, we're going to do that when we step by step through this particular layer. What we've just done is we've replicated this particular layer of the CNN Explainer website. We've still got the relu, we've still got another conv and a relu and a max pool and a conv and a relu and a conv and a relu and a max pool. But this is the block I was talking about. This is one block here of this neural network, or at least that's how I've broken it down. And this is another block. You might notice that they're comprised of the same layers, just stacked on top of each other. And then we're going to have an output layer. And if you want to learn about where the hyperparameters came from, what we just coded, where could you learn about those? Well, one, you could go, of course, to the PyTorch documentation, PyTorch nn-conv2d. You can read about it there. There's the mathematical operation that we talked about or briefly stepped on before, or touched on, stepped on. Is that the right word? So create a conv layer. It's there. But also, this is why I showed you this beautiful website, so that you can read about these hyperparameters down here. Understanding hyperparameters. So your extra curriculum for this video is to go through this little graphic here and see if you can find out what padding means, what the kernel size means, and what the stride means. I'm not going to read through this for you. You can have a look at this interactive plot. We're going to keep coding because that's what we're all about here. If in doubt, code it out. So we're going to now add a relu layer. And then after that, we're going to add another conv2d layer. And the in channels here is going to be the hidden units because we're going to take the output size of this layer and use it as the input size to this layer. We're going to keep going here. Out channels equals hidden units again in this case. And then the kernel size is going to be 3 as well. stride will be 1, padding will be 1. Now, of course, we can change all of these values later on, but just bear with me while we set them how they are. We'll have another ReLU layer, and then we're going to finish off with the NN max pool 2D layer. Again, the 2D comes from the same reason we use conv2D. We're working with 2D data here. And we're going to set the kernel size here to be equal to 2. And of course, this can be a tuple as well, so it can be 2, 2. Now, where could you find out about NN max pool 2D? Well, we go NN max pool 2D. What does this do? Applies a 2D max pooling over an input signal composed of several input planes. So it's taking the max of an input. And we've got some parameters here, kernel size, the size of the window to take the max over. Now, where have we seen a window before? I'm just going to close these. If we come back up, where did we see a window? Let's dive into the max pool layer. See where my mouse is? Do you see that 2 by 2? Well, that's a window. Now look at the difference between the input and the output. What's happening? Well, we have a tile that's 2 by 2, a window of 4, and the max, we're taking the max of that tile. In this case, it's 0. Let's find the actual value. There we go. So if you look at those 4 numbers in the middle, inside the max brackets, we have 0.07, 0.09, 0.06, 0.05, and the max of all those is 0.09. And you'll notice that the input and the output shapes are different. The output is half the size of the input. So that's what max pooling does, is it tries to take the max value of whatever its input is and then outputs it on the right here. And so as our data, this is a trend in all of deep learning actually. As our image moves through, this is what you'll notice. Notice all the different shapes here. Even if you don't completely understand what's going on here, you'll notice that the 2 values here on the left start to get smaller and smaller as they go through the model. And what our model is trying to do here is take the input and learn a compressed representation through each of these layers. So it's going to smush and smush and smush, trying to find the most generalizable patterns to get to the ideal outputs. And that input is eventually going to be a feature vector to our final layer. So a lot going on there, but let's keep coding. What we've just completed is this first block. We've got a conv layer, a ReLU layer, a conv layer, a ReLU layer, and a max pool layer. Look at that. Conv layer, ReLU layer, conv layer, ReLU layer, max pool. Should we move on to the next block? We can do this one a bit faster now because we've already coded the first one. So I'm going to do nn.sequential as well. And then we're going to go nn.conv2d. We're going to set the in channels. What should the in channels be here? Well, we're going to set it to hidden units as well because our network is going to flow just straight through all of these layers. And the output size of this is going to be hidden units. And so we want the in channels to match up with the previous layer's out channels. So then we're going to go out channels equals hidden units as well. We're going to set the kernel size. Kernel size equals 3, stride equals 1, padding equals 1. Then what comes next? Well, because the 2 blocks are identical, the conv block 1 and conv 2, we can just go the exact same combination of layers. NN ReLU, NN conv 2D, in channels equals hidden units, out channels equals, you might already know this, hidden units. Then we have kernel size equals 3, 32, don't want it that big. Stride equals 1, padding equals 1. What comes next? Well, we have another ReLU layer, ReLU, and then what comes after that? We have another max pool. And then max pool 2D, kernel size equals 2. Beautiful. Now, what have we coded up so far? We've got this block, number 1. That's what this 1 on the inside here. And then we have conv 2, ReLU 2, conv 2, ReLU 2, max pool 2. So we've built these 2 blocks. Now what do we need to do? Well, we need an output layer. And so, what did we do before when we made model 1? We flattened the inputs of the final layer before we put them to the last linear layer. So flatten. So this is going to be the same kind of setup as our classifier layer. Now, I say that on purpose because that's what you'll generally hear the last output layer in a classification model called, is a classifier layer. So we're going to have, these two layers are going to be feature extractors. In other words, they're trying to learn the patterns that best represent our data. And then this final layer is going to take those features and classify them into our target classes, whatever our model thinks best suits those features, or whatever our model thinks those features that it learned represents in terms of our classes. So let's code it out. We'll go down here. Let's build our classifier layer. This is our biggest neural network yet. You should be very proud. We have nn.sequential again, and we're going to pass in nn.flatten, because the output of these two blocks is going to be a multi-dimensional tensor, something similar to this size, 13, 13, 10. So we want to flatten the outputs into a single feature vector, and then we want to pass that feature vector to an nn.linear layer. And we're going to go in features equals hidden units times something times something. Now the reason I do this is because we're going to find something out later on, or times 0, just so it doesn't error. But sometimes calculating what your in features needs to be is quite tricky. And I'm going to show you a trick that I use later on to figure it out. And then we have out features, relates to our output shape, which will be the length of how many classes we have, right? One value for each class that we have. And so, with that being said, let's now that we've defined all of the components of our tiny VGG architecture, there is a lot going on, but this is the same methodology we've been using the whole time, defining some components and then putting them together to compute in some way in a forward method. So forward self x. How are we going to do this? Well, we're going to set x is equal to self conv block 1 x. So x is going to go through conv block 1. It's going to go through the conv2d layer, relu layer, conv2d layer, relu layer, max pool layer, which will be the equivalent of an image going through this layer, this layer, this layer, this layer, this layer, and then ending up here. So we'll set it to that, and then we can print out x.shape to get its shape. We'll check this later on. Then we pass x through conv block 2, which is just going to go through all of the layers in this block, which is equivalent to the output of this layer going through all of these layers. And then because we've constructed a classifier layer, we're going to take the output of this block, which is going to be here, and we're going to pass it through our output layer, or what we've termed it, our classifier layer. I'll just print out x.shape here so we can track the shape as our model moves through the architecture. X equals self.classifier x. And then we're going to return x. Woohoo! Look at us go! We just built our first convolutional neural network by replicating what's on a CNN Explainer website. Now, that is actually very common practice in machine learning, is to find some sort of architecture that someone has found to work on some sort of problem and replicate it with code and see if it works on your own problem. You'll see this quite often. And so now let's instantiate a model. We'll go torch.manual C. We're going to instantiate our first convolutional neural network. Model 2 equals fashion mnist. We will go model v2, and we are going to set the input shape. Now, what will the input shape be? Well, our conv2d layer up here, the input shape is the number of channels in our images. So do we have an image ready to go? Image shape. This is the number of color channels in our image. We have 1. If we had color images, we would set the input shape to 3. So the difference between our convolutional neural network, our CNN, tiny VGG, and the CNN Explainer, tiny VGG, is that they are using color images. So their input is 3 here. So 1 for each color channel, red, green, and blue. Whereas we have black and white images, so we have only 1 color channel, so we set the input shape to 1. And then we're going to go hidden units equals 10, which is exactly the same as what tiny VGG has used. 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that sets the hidden units value of each of our layers. That's the power of creating an initializer with hidden units. And then finally, our output shape is going to be what? We've seen this before. This is going to be the length of our class names, one value for each class in our data set. And of course, we're going to send this model to the device. We're going to hit Shift and Enter. Oh no, what did we get wrong? Out channels, output shape. Where did I spell wrong? Out channels, out channels, out channels. I forgot an L. Of course, typo. Oh, kernel size, another typo. Did you notice that? Kernel size, kernel size, kernel size, kernel size. Where did we spell this wrong? Oh, here. Kernel size. Are there any other typos? Probably. Beautiful. There we go. Okay, what have we got? Initializing 0 op tenses is a non-op. Oh, so we've got an issue here, an error here, because I've got this. But this is just to, there's a trick to calculating this. We're going to cover this in another video, but pat yourself on the back. We've written a fair bit of code here. This is a convolutional neural network that replicates the tiny VGG architecture on the CNN Explainer website. Now, don't forget, your extra curriculum is to go through this website for at least 20 minutes and read about what's happening in our models. We're focused on code here, but this is particularly where you want to pay attention to. If you read through this, understanding hyperparameters, and play around with this, the next couple of videos will make a lot more sense. So read about padding, read about kernel size, and read about stride. I'll see you in the next video. We're going to go through our network step by step. Welcome back. Now, I'm super stoked because in the last video, we coded together our first ever convolutional neural network in PyTorch. So, well done. We replicated the tiny VGG architecture from the CNN Explainer website, my favorite place for learning about CNNs in the browser. So now we introduced two new layers that we haven't seen before, conv2d and maxpool2d, but they all have the same sort of premise of what we've been doing so far, is that they're trying to learn the best features to represent our data in some way, shape, or form. Now, in the case of maxpool2d, it doesn't actually have any learnable parameters. It just takes the max, but we're going to step through that later on. Let's use this video to step through nnconv2d. We're going to do that with code. So I'll make a new heading here. 7.1, stepping through nnconv2d. Beautiful. Now, where could we find out what's going on in nnconv2d? Well, of course, we have the documentation, nnconv2d. We've got PyTorch. So if you want to learn the mathematical operation that's happening, we have this value here, this operation here. Essentially, it's saying the output is equal to the bias term times something plus the sum of the weight times something times the input. So do you see how just the weight matrix, the weight tensor, and the bias value manipulating our input in some way equals the output? Now, if we map this, we've got batch size, channels in, height, width, channels out, 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 etc., etc. But we're not going to focus too much on this. If you'd like to read more into that, you can. Let's try it with code. And we're going to reproduce this particular layer here, the first layer of the CNN Explainer website. And we're going to do it with a dummy input. In fact, that's one of my favorite ways to test things. So I'm just going to link here the documentation. See the documentation for nnconv2d here. And if you'd like to read through more of this, of course, this is a beautiful place to learn about what's going on. There's the shape, how to calculate the shape, height out, width out, etc. That's very helpful if you need to calculate input and output shapes. But I'll show you my trick for doing so later on. We have here, let's create some dummy data. So I'm going to set torch manual seed. We need it to be the same size as our CNN Explainer data. So 64, 64, 3, but we're going to do it PyTorch style. This is color channels last. We're going to do color channels first. So how about we create a batch of images? We're going to be writing torch.randn. And we're going to pass in size equals 32, 3, 64, 64. And then we're going to create a singular image by taking the first of that. So image is 0. Now let's get the image batch shape. Because a lot of machine learning, as I've said before, and deep learning is making sure your data has the right shape. So let's check images.shape. And let's check single image shape. We're going to go test image.shape. And finally, we're going to print, what does the test image look like? We'll get this on a new line, hey? New line, test image. This is, of course, not going to be an actual image. It's just going to be a collection of random numbers. And of course, that is what our model is currently comprised of. Model 2, if we have a look at what's on the insides, we are going to see a whole bunch of random numbers. Look at all this. What do we have? We scroll up. Is it going to give us a name for something? We have conv block 22. We have a weight. We have a bias. Keep going up. If we go right to the top, we have another weight. Keep going down. We have a bias, a weight, etc., etc. Now, our model is comprised of random numbers, and what we are trying to do is, just like all of our other models, is pass data in and adjust the random numbers within these layers to best represent our data. So let's see what happens if we pass some random data through one of our conv2D layers. So let's go here. We're going to create a single conv2D layer. So conv layer equals, what does it equal? NN conv2D, and we're going to set the in channels is equal to what? Oh, revealed the answer too quickly. 3. Why is it 3? Well, it's because the in channels is the same number of color channels as our images. So if we have a look at our test image shape, what do we have? 3. It has 3 color channels. That is the same as the value here, except the order is reversed. This is color channels last. PyTorch defaults to color channels first. So, or for now it does. In the future, this may change. So just keep that in mind. So out channels equals 10. This is equivalent to the number of hidden units we have. 1, oh, I don't want that one just yet. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have that 10 there. So we have 10 there. And then we have kernel size. Oh, what is the kernel? Well, it's not KFC, I can tell you that. And then we have stride, and then we have padding. We're going to step through these in a second. But let's check out the kernel. And this kernel can also be 3 by 3. But it's a shortcut to just type in 3. So that's what it actually means if you just type in a single number. It's equivalent to typing in a tuple. Now, of course, you could find that out by reading through the documentation here. But where did I get that value? Well, let's dive into this beautiful website and let's see what's happening. So we have a kernel here, which is also called a filter. So the thing I'm talking about is this little square here, this kernel. Oh, we can see the weights there up the top. This is how beautiful this website is. So if we go over there, this is what's going to happen. This is a convolution. It starts with this little square and it moves pixel by pixel across our image. And you'll notice that the output is creating some sort of number there. And you'll notice in the middle we have a mathematical operation. This operation here is what's happening here. All right, weight times the input. That's what we've got there. Now, the beauty of PyTorch is it does all of this behind the scenes for us. So again, if you'd like to dig more into the mathematical operation behind the scenes, you've got the resource here, and you've also got plenty of other resources online. We're going to focus on code for now. So if we keep doing this across our entire image, we get this output over here. So that's the kernel. And now where did I get 3 by 3 from? Well, look at this. 1, 2, 3, 1, 2, 3, 1, 2, 3. 3 by 3, we have 9 squares. Now, if we scroll down, this was your extra curriculum for the last video. Understanding hyperparameters. What happens if we change the kernel size to 3 by 3? Have a look at the red square on the left. Now, if we change it to 2 by 2, it changed again. 3 by 3, this is our kernel, or also known as a filter, passing across our image, performing some sort of mathematical operation. And now the whole idea of a convolutional layer is to try and make sure that this kernel performs the right operation to get the right output over here. Now, what do these kernels learn? Well, that is entirely up to the model. That's the beauty of deep learning, is that it learns how to best represent our data, hopefully, on its own by looking at more data. And then so if we jump back in here, so that's the equivalent of setting kernel size 3 by 3. What if we set the stride equal to 1? Have we got this in the right order? It doesn't really matter. Let's go through stride next. If we go to here, what does stride say? Stride of the convolution, of the convolving kernel. The default is 1. Wonderful. Now if we set the stride, or if we keep it at 1, it's a default 1, it's going to hop over, watch the red square on the left, it's going to hop over 1 pixel at a time. So the convolution, the convolving, happens 1 pixel at a time. That's what the stride sets. Now, watch what happens when I change the stride value to the output shape. Wow. Do you notice that it went down? So we have here, the kernel size is still the same, but now we're jumping over 2 pixels at a time. Notice how on the left, 2 pixels become available, and then if I jump over again, 2 pixels. So the reason why the output compresses is because we're skipping some pixels as we go across the image. And now this pattern happens throughout the entire network. That's one of the reasons why you see the size of our input, or the size of each layer, go down over time. What our convolutional layer is doing, and in fact a lot of deep learning neural networks do, is they try to compress the input into some representation that best suits the data. Because it would be no point of just memorizing the exact patterns. You want to compress it in some way. Otherwise, you just might as well move your input data around. You want to learn generalizable patterns that you can move around. And so we keep going. We've got padding equals 0. Let's see what happens here. If we change the padding value, what happens? Up, down. Notice the size here. Oh, we've added 2 extra pixels around the edge. Now if we go down, 1 extra pixel. Now if we go 0. Now why might we do that? If we add some padding on the end, well that's so that our kernel can operate on what's going on here in the corner, in case there's some information on the edges of our image. Now you might be thinking, Daniel, there's a whole bunch of values here. How do we know what to set them? Well, you notice that I've just copied exactly what is going on here. There's a 3 by 3 kernel, there's no padding on the image, and the stride is just going 1 by 1. And so that's often very common in machine learning, is that when you're just getting started and you're not sure what values to set these values to, you just copy some existing values from somewhere and see if it works on your own problem. And then if it doesn't, well, you can adjust them. So let's see what happens when we do that. So pass the data through the convolutional layer. So let's see what happens. Conv output equals conv layer. Let's pass it our test image. And we'll check the conv output. What happens? Oh no, we get an error. Oh, of course we get a shape error, one of the most common issues of machine learning and deep learning. So this is saying that our input for the conv layer expects a 4-dimensional tensor, except it got a 3-dimensional input size of 364, 64. Now how do we add an extra dimension to our test image? Let's have a look. How would we add a batch dimension over on the left here? We can go unsqueeze 0. So now we have a 4-dimensional tensor. Now, just keep in mind that if you're running this layer, nnconv2d, on a PyTorch version that is, I believe they fixed this or they changed it in PyTorch, what am I on? I think this Google Colab instance is on 1.10. I think you might not get this error if you're running 1.11, so just keep that in mind. Like this should work if you're running 1.11. But if it doesn't, you can always unsqueeze here. And let's see what happens. Look at that. We get another tensor output. Again, this is just all random numbers though, because our test image is just random numbers. And our conv layer is instantiated with random numbers. But we'll set the manual seed here. Now, if our numbers are different to if your numbers are different to what's on my screen, don't worry too much. Why is that? Because our conv layer is instantiated with random numbers, and our test image is just random numbers as well. What we're paying attention to is the input and output shapes. Do you see what just happened? we put our input image in there with 3 channels. And now, because we've set out channels to be 10, we've got 10, and we've got 62, 62. And this is just the batch size. It just means 1 image. So essentially, our random numbers, our test image, have gone through the convolutional layer that we created, have gone through this mathematical operation with regards to all the values that we've set. We've put the weight tensor, well, actually, PyTorch created that for us. PyTorch has done this whole operation for us. Thank you, PyTorch. It's gone through all of these steps across. You could code this all by hand if you want, but it's a lot easier and simpler to use a PyTorch layer. And it's done this, and now it's created this output. Now, whatever this output is, I don't know. It is random numbers, but this same process will happen if we use actual data as well. So let's see what happens if we change the values. Kernel size we increase. Notice how our output has gotten smaller because we're using a bigger kernel to convolve across the image. What if we put this to 3.3, back to what it was, and stride of 2? What do you think will happen? Well, our output size basically halves because we're skipping 2 pixels at a time. We'll put that back to 1. What do you think will happen if we set padding to 1? 64, 64. We get basically the same size because we've added an extra pixel around the edges. So you can play around with this, and in fact, I encourage you to do. This is what we just did. Padding 1. We just added an extra dummy 0 pixel around the edges. So practice with this. See what happens as you pass our test image, random numbers, through a conv2D layer with different values here. What do you think will happen if you change this to 64? Give that a shot, and I'll see you in the next video. Who's ready to step through the NN max pool 2D layer? Put your hand up. Well, I've got my hand up, so let's do it together, hey? We've got 7.2. Now, you might have already given this a shot yourself. Stepping through NN max pool 2D. And this is what I do for a lot of different concepts that I haven't gone through before, is I just write some test code and see what the inputs and outputs are. And so where could we find out about max pool 2D? Well, of course, we've got the documentation. I'm just going to link this in here. Max pool 2D. In the simplest case, the output value of layer with input size NCHW, output NCHout, W out. By the way, this is number of batches, color channels, height, width, and this is the output of that layer. And kernel size, which is a parameter up here, KHKW, can be precisely described as out is going to be the max of some value, depending on the kernel size and the stride. So let's have a look at that in practice. And of course, you can read further through the documentation here. I'll just grab the link for this actually. So it's here. Wonderful. And let's now first try it with our test image that we created above. So just highlight what the test image is. Bunch of random numbers in the same shape as what a single image would be if we were to replicate the image size of the CNN explainer. By the way, we'll have a look at a visual in a second of max pool here, but you can go through that on your own time. Let's, if in doubt, code it out. So we're going to print out the original image shape without unsqueezed dimension. Because recall that we had to add an extra dimension to pass it through our conv2D layer. Now, if you're using a later version of PyTorch, you might not get an error if you only use a 3-dimensional image tensor and pass it through a conv layer. So we're going to pass it in test image original shape, test image dot shape. So this is just going to tell us what the line of code in the cell above tells us, but that's fine. I like to make pretty printouts, you know. Test image with unsqueezed dimension. So this is just going to be our test image, and we're going to see what happens when we unsqueeze a dimension. Unsqueeze on the 0th dimension, that is. I was about to say first, but it's the 0th. Now we're going to create a sample NN max pool 2D layer. Because remember, even layers themselves in torch.nn are models of their own accord. So we can just create a single, this is like creating a single layer model here. We'll set the kernel size equal to 2. And recall, if we go back to CNN Explainer, kernel size equal to 2 results in a 2 by 2 square, a 2 by 2 kernel that's going to convolve over our image, like so. And this is an example input and example output. And you can see the operation that max pooling does here. So just keep that in mind as we pass some sample data through our max pool layer. And now let's pass data through it. Or actually, we'll pass it through just the conv layer first. Through just the conv layer. Because that's sort of how you might stack things. You might put a convolutional layer and then a max pool layer on top of that convolutional layer. So test image through conv. We'll create a variable here. Equals our conv layer. Is going to take as an input our test image dot unsqueeze on the 0th dimension again. Beautiful. Now we're going to print out the shape here. This is just highlighting how I like to troubleshoot things. Is I do one step, print the shape. One step, print the shape. See what is happening as our data moves through various layers. So test image through conv.shape. We'll see what our conv layer does to the shape of our data. And then we're going to pass data through the max pool layer, which is the layer we created a couple of lines above, this one here. So let's see what happens. Test image through, can't type at the moment, through conv and max pool. So quite a long variable name here, but this is to help us avoid confusion of what's going on. So we go test image through conv. So you notice how we're taking the output of our convolutional layer, this here, and we're passing it through our max pool layer, which has another typo. Wonderful. And finally, we'll print out the shape after going through conv layer and max pool layer. What happens here? So we want test image through conv and max pool. Let's see how our max pool layer manipulates our test image's shape. You ready? 3, 2, 1, let's go. What do we get? Okay, so we have the test image original shape. Recall that our test image is just a collection of random numbers. And of course, our conv layer is going to be instantiated with random numbers. And max pool actually has no parameters. It just takes the maximum of a certain range in a tensor. So when we unsqueeze the test image as the input, we get an extra dimension here. When we pass it through our conv layer, oh, where did this 64 come from? 1, 64, 64, 64. Let's go back up to our conv layer. Do you notice how that we get the 64 there because we changed the out channels value? If we change this back to 10, like what's in the CNN explainer model, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, what do you think will happen there? Well, we get a little highlight here, 10. Then we keep going. I'll just get rid of this extra cell. We don't need to check the version anymore. We'll check the test image shape, still 3, 64, 64. But then as we pass it through the conv layer here, we get a different size now. So it originally had 3 channels as the input for color channels, but we've upscaled it to 10 so that we have 10 hidden units in our layer. And then we have 64, 64. Now, again, these shapes will change if we change the values of what's going on here. So we might put padding to 0. What happens there? Instead of 64, 64, we get 62, 62. And then what happens after we pass it through the conv layer and then through the max pool layer? We've got 1, 10, 64, 64. And now we have 1, 10, 32, 32. Now, why is that? Well, let's go back into the CNN explainer, jump into this max pool layer here. Maybe this one because it's got a bit more going on. Do you notice on the left here is the input? And we've got a 2 by 2 kernel here. And so the max pooling layer, what it does is it takes the maximum of whatever the input is. So you'll notice the input is 60, 60 in this case. Whereas the output over here is 30, 30. Now, why is that? Well, because the max operation here is reducing it from section of 4 numbers. So let's get one with a few different numbers. There we go, that'll do. So it's taking it from 4 numbers and finding the maximum value within those 4 numbers here. Now, why would it do that? So, as we've discussed before, what deep learning neural network is trying to do, or in this case a CNN, is take some input data and figure out what features best represent whatever the input data is and compress them into a feature vector that is going to be our output. Now, the reason being for that is because you could consider it from a neural network's perspective is that intelligence is compression. So you're trying to compress the patterns that make up actual data into a smaller vector space, go from a higher dimensional space to a smaller vector space in terms of dimensionality of a tensor. But still, this smaller dimensionality space represents the original data and can be used to predict on future data. So that's the idea behind max pool is, hey, if we've got these learned features from our convolutional layers, will the most important patterns stay around if we just take the maximum of a certain section? So do you notice how the input here, you can still see the outline of the car here, albeit a little bit more pixelated. But just by taking the max of a certain region, we've got potentially the most important feature of that little section. And now, of course, you could customize this value here. When we create our max pool layer, you could increase the kernel size to 4 by 4. What do you think will happen if we can increase it to 4? So here we've got a 2 by 2 kernel. If we increase it to 4 by 4, what happens? Do you notice that we've gone from 62 to 15? We've essentially divided our feature space by 4. We've compressed it even further. Now, will that work? Well, I'm not sure. That's part of the experimental nature of machine learning, but we're going to keep it at 2 for now. And so this is with our tensor here, 64, 64. But now let's do the same as what we've done above, but we'll do it with a smaller tensor so that we can really visualize things. And we're going to just replicate the same operation that's going on here. So let's go here. We'll create another random tensor. We'll set up the manual seed first. And we're going to create a random tensor with a similar number of dimensions. Now recall, dimensions don't tell you, so this is a dimension. 1, 3, 64, 64. That is a dimension. Now dimensions can have different values within themselves. So we want to create a 4-dimensional tensor to our images. So what that means is, let me just show you. It's way easier to explain things when we've got code. Is torch.randn, and we're going to set it up as size equals 1, 1, 2, 2. We can have a look at this random tensor. It's got 4 dimensions. 1, 2, 3, 4. So you could have a batch size, color channels, and height, width. A very small image, but it's a random image here. But this is quite similar to what we've got going on here, right? 4 numbers. Now, what do you think will happen if we create a max pool layer, just like we've done above? Create a max pool layer. So we'll go max pool layer. Just repeating the code that we have in the cell above, that's all right. A little bit of practice. Kernel size equals 2. And then we're going to pass the random tensor through the max pool layer. So we'll go max pool tensor equals max pool layer, and we're going to pass it in the random tensor. Wonderful. And then we can print out some shapes and print out some tensors, as we always do, to visualize, visualize, visualize. So we're going to write in here max pool tensor on a new line. We'll get in the max pool tensor. We'll see what this looks like. And we'll also print out max pool tensor shape. And we could probably print out random tensor itself as well as its shape as well. We'll get the shape here, dot shape. And we'll do the same for the random tensor. So print, get a new line, random tensor, new line, random tensor, and then we'll get the shape. random tensor shape, random tensor. Oh, a lot of coding here, but that's the fun part about machine learning, right? You get to write lots of code. Okay, so we're visualizing what's going on with our random tensor. This is what's happening within the max pool layer. We've seen this from a few different angles now. So we have a random tensor of numbers, and we've got a size here. But the max pool tensor, once we pass our random tensor through the max pool layer, what happens? Well, we have 0.3367, 1288, 2345, 2303. Now, what's the max of all these? Well, it takes the max here, is 3367. Oh, and we've got the random tensor down there. We don't want that. And see how we've reduced the shape from 2 by 2 to 1 by 1? Now, what's going on here? Just for one last time to reiterate, the convolutional layer is trying to learn the most important features within an image. So if we jump into here, now what are they? Well, we don't decide what the convolutional layer learns. It learns these features on its own. So the convolutional layer learns those features. We pass them through a ReLU, nonlinear activation, in case our data requires nonlinear functions. And then we pass those learned features through a max pool layer to compress them even further. So the convolutional layer can compress the features into a smaller space, but the max pooling layer really compresses them. So that's the entire idea. One more time, we start with some input data, we design a neural network, in this case a convolutional neural network, to learn a compressed representation of what our input data is, so that we can use this compressed representation to later on make predictions on images of our own. And in fact, you can try that out if you wanted to. Click here and add your own image. So I'd give that a go. That's your extension for this video. But now we've stepped through the max pool 2D layer and the conv 2D layer. I think it's time we started to try and use our tiny VGG network. This is your challenge, is to create a dummy tensor and pass it through this model. Pass it through its forward layer and see what happens to the shape of your dummy tensor as it moves through conv block 1 and conv block 2. And I'll show you my trick to calculating the in features here for this final layer, which is equivalent to this final layer here. I'll see you in the next video. Over the last few videos, we've been replicating the tiny VGG architecture from the CNN Explainer website. And I hope you know that this is actually quite exciting, because years ago, this would have taken months of work. And we've broken it down over the last few videos and rebuilt it ourselves with a few lines of PyTorch code. So that just goes to show how powerful PyTorch is and how far the deep learning field has come. But we're not finished yet. Let's just go over to our keynote. This is what we've done. CNN Explainer model. We have an input layer. We've created that. We have conv2D layers. We've created those. We have ReLU activation layers. We've created those. And finally, we have pooling layers. And then we finish off with an output layer. But now let's see what happens when we actually pass some data through this entire model. And as I've said before, this is actually quite a common practice, is you replicate a model that you found somewhere and then test it out with your own data. So we're going to start off by using some dummy data to make sure that our model works. And then we're going to pass through, oh, I've got another slide for this. By the way, here's a breakdown of torch and conv2D, if you'd like to see it in text form. Nothing here that we really haven't discussed before, but this will be in the slides if you would like to see it. Then we have a video animation. We've seen this before though, and plus, I'd rather you go through the CNN Explainer website on your own and explore these different values rather than me just keep talking about it. Here's what we're working towards doing. We have a fashion MNES dataset, and we have our inputs. We're going to numerically encode them. We've done that already. Then we have our convolutional neural network, which is a combination of convolutional layers, nonlinear activation layers, pooling layers. But again, these could be comprised in many different ways, shapes, and forms. In our case, we've just replicated the tiny VGG architecture. And then finally, we want to have an output layer to predict what class of clothing a particular input image is. And so let's go back. we have our CNN model here, and we've got model 2. So let's just practice a dummy forward pass here. We're going to come back up a bit to where we were. We'll make sure we've got model 2. And we get an error here because I've times this by 0. So I'm going to just remove that and keep it there. Let's see what happens if we create a dummy tensor and pass it through here. Now, if you recall what our image is, do we have image? This is a fashion mnist image. So I wonder if we can go plot.imshow image, and I'm going to squeeze that, and I'm going to set this CMap equal to gray. So this is our current image. Wonderful. So there's our current image. So let's create a tensor. Or maybe we just try and pass this through the model and see what happens. How about we try that? Model, image. All right, we're going to try the first pass, forward pass. So pass image through model. What's going to happen? Well, we get an error. Another shape mismatch. We've seen this before. How do we deal with this? Because what is the shape of our current image? 128, 28. Now, if you don't have this image instantiated, you might have to go back up a few cells. Where did we create image? I'll just find this. So we created this a fairly long time ago. So I'm going to probably recreate it down the bottom. My goodness, we've written a lot of code. Well done to us. We could create a dummy tensor if we wanted to. How about we do that? And then if you want to find, oh, right back up here, we have an image. How about we do that? We can just do it with a dummy tensor. That's fine. We can create one of the same size. But if you have image instantiated, you can try that out. So there's an image. Let's now create an image that is, or a random tensor that is the same shape as our image. So rand image tensor equals what? Torch.randn, and we're going to pass in size equals 1, 28, 28. Then if we get rand image tensor, we check its shape, what do we get? So the same shape as our test image here, but it's just going to be random numbers, but that's okay. We just want to highlight a point here of input and output shapes. We want to make sure our model works. Can our random image tensor go all the way through our model? That's what we want to find out. So we get an error here. We have 4 dimensions, but our image is 3 dimensions. How do we add an extra dimension for batch size? Now, you might not get this error if you're running a later version of PyTorch. Just keep that in mind. So unsqueeze 0. Oh, expected all tensors to be on the same device, but found at least 2 devices. Again, we're going through all the 3 major issues in deep learning. Shape mismatch, device mismatch, data type mismatch. So let's put this on the device to target device, because we've set up device agnostic code. Map 1 and map 2 shapes cannot be multiplied. Oh, but we get an output here. That is very exciting. So what I might do is move this a couple of cells up so that we can tell what's going on. I'm going to delete this cell. So where do these shapes come from? Well, we've printed out the shapes there. And so this is what's happened when I'll just create our random tensor. I'll bring our random tensor up a bit too. Let's bring this up. There we go. So we pass our random image tensor through our model, and we've made sure it's got 4 dimensions by unsqueeze 0. And we make sure it's on the same device as our model because our model has been sent to the GPU. And this is what happens as we pass our random image tensor. We've got 128, 28 instead of previously we've seen 64, 64, 3. Just going to clean this up a bit. And we get different shapes here. So you'll notice that as our input, if it was 64, 64, 3, goes through these layers, it gets shaped into different values. Now, this is going to be universal across all of the different data sets you work on. You will be working with different shapes. So it's important to, and also quite fun, to troubleshoot what shapes you need to use for your different layers. So this is where my trick comes in. To find out the shapes for different layers, I often construct my models, how we've done here, as best I can with the information that I've got. such as replicating what's here, but I don't really know what the output shape is going to be before it goes into this final layer. And so I recreate the model as best I can, and then I pass data through it in the form of a dummy tensor in the same shape as my actual data, so we could customize this to be any shape that we wanted. And then I print the shapes of what's happening through each of the forward pass steps. And so if we pass it through this random tensor through the first conv block, it goes through these layers here, and then it outputs a tensor with this size. So we've got 10 because that's how many output channels we've set, and then 14, 14 because our 28, 28 tensor has gone through a max pool 2D layer and gone through a convolutional layer. And then it goes through the next block, conv block 2, which is because we've put it in the forward method here. And then it outputs the shape, and if we go back down, we have now a shape of 1, 10, 7, 7. So our previous tensor, the output of conv block 1, has gone from 14, 14 to 7, 7. So it's been compressed. So let me just write this down here. Output shape of conv block 1, just so we get a little bit more information. And I'm just going to copy this, put it in here. That will be conv block 2. And then finally, I want to know if I get an output shape of classifier. So if I rerun all of this, I don't get an output shape of classifier. So my model is running into trouble once it gets to, so I get the output of conv block 1. I don't get an output of classifier. So this is telling me that I have an issue with my classifier layer. Now I know this because, well, I've coded this model before, and the in features here, we need a special calculation. So what is going on with our shapes? mat1 and mat2 shapes cannot be multiplied. So do you see here, what is the rule of matrix multiplication? The inner dimensions here have to match. We've got 490. Where could that number have come from? And we've got 10 times 10. Now, okay, I know I've set hidden units to 10, so maybe that's where that 10 came from. And what is the output layer or the output shape of conv block 2? So if we look, we've got the output shape of conv block 2. Where does that go? The output of conv block 2 goes into our classifier model, and then it gets flattened, so that's telling us something there. And then our NN linear layer is expecting the output of the flattened layer as its in features. So this is where my trick comes into play. I pass the output of conv block 2 into the classifier layer. It gets flattened, and then that's what my NN.linear layer is expecting. So what happens if we flatten this shape here? Do we get this value? Let's have a look. So if we go 10 times 7 times 7, 490. Now, where was this 10? Well, that's our hidden units. And where were these 7s? Well, these 7s are the output of conv block 2. So that's my trick. I print the shapes of previous layers and see whether or not they line up with subsequent layers. So if we go times 7 times 7, we're going to have hidden units equals 10 times 7 times 7. Where do we get the two 7s? Because that is the output shape of conv block 2. Do you see how this can be a little bit hard to calculate ahead of time? Now, you could calculate this by hand if you went into nconv2d, but I prefer to write code to calculate things for me. You can calculate that value by hand if you go through h out, w out. You can add together all of the different parameters and multiply them and divide them and whatnot. You can calculate the input and output shapes of your convolutional layers. You're more than welcome to try that out by hand, but I prefer to code it out. If in doubt, code it out. Now let's see what happens if we run our random image tensor through our model now. Do you think it will work? Well, let's find out. All we've done is we've added this little line here, times 7 times 7. And we've calculated that because we've gone, What if we pass a tensor of this dimension through a flattened layer? And what is our rule of matrix multiplication? The inner dimensions here must match. And why do we know that these are matrices? Well, mat1 and mat2 shapes cannot be multiplied. And we know that inside a linear layer is a matrix multiplication. So let's now give this a go. We'll see if it works. Oh, would you look at that? That is so exciting. We have the output shape of the classifier is 1 and 10. We have a look, we have one number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. One number for each class in our data set. Wow. Just like the CNN Explainer website, we have 10 outputs here. We just happen to have 10 classes as well. Now, this number again could be whatever you want. It could be 100, could be 30, could be 3, depending on how many classes you have. But we have just figured out the input and output shapes of each layer in our model. So that's very exciting. I think it's now time. We've passed a random tensor through. How about we pass some actual data through our model? In the next video, let's use our train and test step functions to train our first convolutional neural network. I'll see you there. Let's get ready to train our first CNN. So what do we need? Where are we up to in the workflow? Well, we've built a model and we've stepped through it. We know what's going on, but let's really see what's going on by training this CNN, or see if it trains, because we don't always know if it will, on our own data set, which is of fashion MNIST. So we're going to set up a loss function and optimizer for model 2, just as we've done before. For model 2, turn that into Markdown. I'll just show you the workflow again. So this is what we're doing. We've got some inputs, we've got a numerical encoding, we've built this architecture, and hopefully it helps us learn, or it helps us make a predictive model that we can input images such as grayscale images of clothing and predict. And if we look where we are at the PyTorch workflow, we've got our data ready. We've built our next model. Now here's where we're up to. Picking a loss function and an optimizer. So let's do that, hey? Loss function, or we can do evaluation metrics as well. So set up loss function / eval metrics / optimizer. And we want from helper functions, import accuracy function. We don't need to re-import it, but we're going to do it anyway for completeness. Loss function equals nn.cross entropy loss, because we are working with a multi-class classification problem. And the optimizer, we're going to keep the same as what we've used before, torch.optim sgd, and we'll pass it in this time. The params that we're trying to optimize are the parameters of model 2 parameters, and we'll use a learning rate of 0.1. Run that, and just to reiterate, here's what we're trying to optimize. Model 2 state dict. We have a lot of random weights in model 2. Have a look at all this. There's the bias, there's the weight. We're going to try and optimize these to help us predict on our fashion MNIST dataset. So, without any further ado, let's in the next video, go to the workflow. We're going to build our training loop, but thanks to us before, we've now got functions to do this for us. So if you want to give this a go, use our train step and test step function to train model 2. Try that out, and we'll do it together in the next video. We're getting so close to training our model. Let's write some code to train our first CNN model. Training and testing. I'm just going to make another heading here. Model 2, using our training and test functions. Woohoo! So we don't have to rewrite all of the steps in a training loop and a testing loop, because we've already created that functionality before through our train step function. There we go. Performs a training, or this should be performs a training step with model trying to learn on data loader. So let's set this up. I'm going to set up torch manual seed 42, and we can set up a CUDA manual seed as well, just to try and make our experiments as reproducible as possible, because we're going to be using CUDA. We're going to measure the time because we want to compare our models, not only their performance in evaluation metrics, but how long they take to train from time it, because there's no point having a model that performs really, really well, but takes 10 times longer to train. Well, maybe there is, depending on what you're working on. Model 2 equals timer. And we're going to train and test model, but that the time is just something to be aware of, is that usually a better performing model will take longer to train. Not always the case, but just something to keep in mind. So for epoch, we're going to use TQDM to measure the progress. We're going to create a range of epochs. We're just going to train for 3 epochs, keeping our experiments short for now, just to see how they work. Epoch. And we're going to print a new line here. So for an epoch in a range, we're going to do the training step, which is our train step function. The model is going to be equal to model 2, which is our convolutional neural network, our tiny VGG. The data loader is just going to be equal to the train data loader, the same one we've used before. The loss function is going to be equal to the loss function that we've set up above, loss fn. The optimizer as well is going to be the optimizer, in our case, stochastic gradient descent. Optimizer equals optimizer. Then we set up the accuracy function, which is going to be equal to our accuracy function. And the device is going to be the target device. How easy was that? Now we do the same for the train, or the testing step, sorry. The model is going to be equal to model 2. And then the data loader is going to be the test data loader. And then the loss function is going to be our same loss function. And then we have no optimizer for this. We're just going to pass in the accuracy function here. And then of course, the device is going to be equal to the device. And then, what do we do now? Well, we can measure the end time, so that we know how long the code here took to run. So let's go train time end for model 2. This will be on the GPU, by the way, but this time it's using a convolutional neural network. And the total train time for model 2 is going to be equal to print train time, our function that we created before as well, to help us measure start and end time. So we're going to pass in train time start, model 2, and then end is going to be train time end model 2. And then we're going to print out the device that it's using as well. So you ready? Are you ready to train our first convolutional neural network? Hopefully this code works. We've created these functions before, so it should be all right. But if in doubt, code it out. If in doubt, run the code. Let's see what happens. Oh my goodness. Oh, of course. Oh, we forgot to comment out the output shapes. So we get a whole bunch of outputs for our model because what have we done? Back up here, we forgot to. So this means every time our data goes through the forward pass, it's going to be printing out the output shapes. So let's just comment out these. And I think this cell is going to take quite a long time to run because it's got so many printouts. Yeah, see? Streaming output truncated to the last 5,000 lines. So we're going to try and stop that. Okay, there we go. Beautiful. That actually worked. Sometimes it doesn't stop so quickly. So we're going to rerun our Fashion MNIST v2 model cell so that we comment out these print lines. And then we'll just rerun these cells down here. Just go back through. Fingers crossed there's no errors. And we'll train our model again. Beautiful. Not as many printouts this time. So here we go. Our first CNN is training. How do you think it'll go? Well, that's why we have printouts, right? So we can see the progress. So you can see here all of the functions that are being called behind the scenes from PyTorch. So thank you to PyTorch for that. There's our train step function was in there. Train step, wonderful. Beautiful. So there's epoch 0. Oh, we get a pretty good test accuracy. How good is that? Test accuracy is climbing as well. Have we beaten our baseline? We're looking at about 14 seconds per epoch here. And then the final epoch, what do we finish at? Oh, 88.5. Wow, in 41.97979 or 42 thereabouts seconds. Again, your mileage may vary. Don't worry too much if these numbers aren't exactly the same on your screen, and same with the training time, because we might be using slightly different hardware. What GPU do I have today? I have a Tesla P100 GPU. You might not have the same GPU, so the training time, if this training time is something like 10 times higher, you might want to look into what's going on. And if these values are like 10% lower or 10% higher, you might want to see what's going on with your code as well. But let's now calculate our Model 2 results. I think it is the best performing model that we have so far. Let's get a results dictionary. Model 2 results. This is so exciting. We're learning the power of convolutional neural networks. Model 2 results equals a val model, and this is a function that we've created before. So returns a dictionary containing the results of a model predicting on data loader. So now let's pass in the model, which will be our trained model 2, and then we'll pass in the data loader, which will be our test data loader. And then, oh, excuse me, typo. Our loss function will be, of course, our loss function, and the accuracy function will be accuracy function. And the device is already set, but we can reset it anyway. Device equals device. And we'll check out the Model 2 results. Make some predictions. Ho-ho, look at that. Model accuracy, 88. Does that beat our baseline? Model 0 results. Oh, we did beat our baseline with a convolutional neural network. All right, so I feel like that's quite exciting. But now let's keep going on, and let's start to compare the results of all of our models. I'll see you in the next video. Welcome back. Now, in the last video, we trained our first convolutional neural network, and from the looks of things, it's improved upon our baseline. But let's make sure by comparing, this is another important part of machine learning experiments, is comparing the results across your experiments. So, and training time. Now, we've done it in a way where we've got 3 dictionaries here of our Model 0 results, Model 1 results, Model 2 results. So, how about we create a data frame comparing them? So, let's import pandas as PD, and we're going to compare results equals pd.dataframe. And because our model results dictionaries all have the same keys, let's pass them in as a list. So Model 0 results, Model 1 results, and Model 2 results to compare them. Wonderful. And what it looks like when we compare the results. Alrighty. So recall our first model was our baseline V0. It was just 2 linear layers. And so we have an accuracy of 83.4 and a loss of 0.47. The next model was we trained on the GPU and we introduced nonlinearities. So we actually found that that was worse off than our baseline. But then we brought in the big guns. We brought in the tiny VGG architecture from the CNN Explainer website and trained our first convolutional neural network. And we got the best results so far. But there's a lot more experiments that we could do. We could go back through our tiny VGG and we could increase the number of hidden units. Where do we create our model? Up here. We could increase this to say 30 and see what happens. That would be a good experiment to try. And if we found that nonlinearities didn't help with our second model, we could comment out the ReLU layers. We could, of course, change the kernel size, change the padding, change the max pool, a whole bunch of different things that we could try here. We could train it for longer, so maybe if we trained it for 10 epochs, it would perform better. But these are just things to keep in mind and try out. I'd encourage you to give them a go yourself. But for now, we've kept all our experiments quite the same. How about we see the results? We add in the training time, because that's another important thing that we've been tracking as well. So we'll add training time to results comparison. So the reason why we do this is because if this model is performing quite well even compared to our CNN, so a difference in about 5% accuracy. Maybe that's tolerable in the space that we're working, except that this model might actually train and perform inference 10 times faster than this model. So that's just something to be aware of. It's called the performance speed trade-off. So let's add another column here, compare results, and we're going to add in, oh, excuse me, got a little error there, that's all right. Got trigger happy on the shift and enter. Training time equals, we're going to add in, we've got another list here, is going to be total train time for model 0 and total train time for model 1 and total train time for model 2. And then we have a look at our compare results dictionary, compare results data frame. Wonderful. So we see, and now this is another thing, I keep stressing this to keep in mind. If your numbers aren't exactly of what I've got here, don't worry too much. Go back through the code and see if you've set up the random seeds correctly. You might need a CUDA random seed. We may have missed one of those. If your numbers are outlandishly different to these numbers, then you should go back through your code and see if there's something wrong. And again, the training time will be highly dependent on the compute environment you're using. So if you're running this notebook locally, you might get faster training times. If you're running it on a different GPU to what I have, NVIDIA SMI, you might get different training times. So I'm using a Tesla P100, which is quite a fast GPU, but that's because I'm paying for Colab Pro, which generally gives you faster GPUs. And model 0 was trained on the CPU. So depending on what compute resource Google allocates to you with Google Colab, this number might vary here. So just keep that in mind. These values, training time, will be very dependent on the hardware you're using. But if your numbers are dramatically different, well, then you might want to change something in your code and see what's going on. And how about we finish this off with a graph? So let's go visualize our model results. And while we're doing this, have a look at the data frame above. Is the performance here, 10 seconds longer training time, worth that extra 5% of the results on the accuracy? Now, in our case, we're using a relatively toy problem. What I mean by toy problem is quite a simple data set to try and test this out. But in your practice, that may be worth doing if your model takes longer to train, but gets quite a bit better performance. It really depends on the problem you're working with. Compare results, and we're going to set the index as the model name, because I think that's what we want our graph to be. We want the model name, and then we're going to plot, we want to compare the model accuracies, and we want to plot the kind is going to be equal to bar H, horizontal bar chart. We'll go P X label, we're going to get accuracy as a percentage, and then we're going to go PY label. This is just something that you could share if someone was asking, how did your modeling experiments go on Fashion MNIST? Well, here's what I've got. And then they ask you, well, what's the Fashion MNIST model V2? Well, you could say that's a convolutional neural network that replicates the CNN Explainer website that trained on a GPU. They go, how long did that take to train? Well, then you've got the training time here. We could just do it as a vertical bar chart. I did it as horizontal so that this looks a bit funny to me. So horizontal like that. So the model names are over here. Wonderful. So now I feel like we've got a trained model. How about we make some visual predictions? Because we've just got numbers on a page here, but our model is trained on computer vision data. And the whole point of making a machine learning model on computer vision data is to be able to visualize predictions. So let's give that a shot, hey? In the next video, we're going to use our best performing model, Fashion MNIST model V2, to make predictions on random samples from the test data set. You might want to give that a shot. Make some predictions on random samples from the test data set and plot them out with their predictions as the title. So try that out. Otherwise, we'll do it together in the next video. In the last video, we compared our model's results. We tried 3 experiments. One was a basic linear model, one was a linear model with nonlinear activations, and Fashion MNIST model V2 is a convolutional neural network. And we saw that from an accuracy perspective, our convolutional neural network performed the best. However, it had the longest training time. And I just want to exemplify the fact that the training time will vary depending on the hardware that you run on. We spoke about this in the last video. However, I took a break after finishing the last video, reran all of the cells that we've written, all of the code cells up here, by coming back to the notebook and going run all. And as you'll see, if you compare the training times here to the last video, we get some different values. Now, I'm not sure exactly what hardware Google Colab is using behind the scenes, but this is just something to keep in mind. At least from now on, we know how to track our different variables, such as how long our model takes to train and what its performance values are. But it's time to get visual. So let's create another heading. Make and evaluate. This is one of my favorite steps after training a machine learning model. So make and evaluate random predictions with the best model. So we're going to follow the Data Explorer's motto of getting visual, 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 or visualize, visualize, visualize. Let's make a function called make predictions. And it's going to take a model, which will be a torch nn.module type. It's also going to take some data, which can be a list. It'll also take a device type, which will be torch.device, and we'll set that by default to equal the default device that we've already set up. And so what we're going to do is create an empty list for prediction probabilities, because what we'd like to do is just take random samples from the test data set, make predictions on them using our model, and then plot those predictions. We want to visualize them. And so we'll also turn our model into evaluation mode, because if you're making predictions with your model, you should turn on evaluation mode. We'll also switch on the inference mode context manager, because predictions is another word for inference. And we're going to loop through for each sample in data. Let's prepare the sample. So this is going to take in a single image. So we will unsqueeze it, because we need to add a batch size dimension on the sample. We'll set dim equals to 0, and then we'll pass that to the device. So add a batch dimension, that's with the unsqueeze, and pass to target device. That way, our data and model are on the same device, and we can do a forward pass. Or we could actually up here go model.toDevice. That way we know that we've got device agnostic code there. Now let's do the forward pass. Forward pass, model outputs raw logits. So recall that if we have a linear layer at the end of our model, it outputs raw logits. So pred logit for a single sample is going to equal model. We pass the sample to our target model, and then we're going to get the prediction probability. How do we get the prediction probability? So we want to go from logit to prediction probability. Well, if we're working with a multi-class classification problem, we're going to use the softmax activation function on our pred logit, and we're going to squeeze it so it gets rid of an extra dimension, and we're going to pass in dim equals 0. So that's going to give us our prediction probability for a given sample. Now, let's also turn our prediction probabilities into prediction labels. So get pred, well actually, I think we're just going to return the pred probs. Yeah, let's see what that looks like, because we've got an empty list up here for pred probs. So for matplotlib, we're going to have to use our data on the CPU. So let's make sure it's on the CPU, because matplotlib doesn't work with the GPU. So get pred prob off GPU for further calculations. So we'll just hard code it in here to make sure that our prediction probability is off the GPU. So pred probs, which is our list up here, we're going to append the pred prob that we just calculated, but we're going to put it on the CPU. And then let's go down here, and we're going to, so if we've done it right, we're going to have a list of prediction probabilities relating to particular samples. So we're going to stack the pred probs to turn list into a tensor. So this is only one way of doing things. There are many different ways that you could make predictions and visualize them. I'm just exemplifying one way. So we're going to torch stack, which is just going to say, hey, concatenate everything in the list to a single tensor. So, we might need to tab that over. Tab, tab. Beautiful. So let's try this function in action and see what happens. I'm going to import random, and then I'm going to set the random seed to 42. And then I'm going to create test samples as an empty list because we want a list of test samples to iterate through. And I'm going to create test labels also as an empty list so that, remember, when we are evaluating predictions, we want to compare them to the ground truth. So we want to get some test samples, and then we want to get their actual labels so that when our model makes predictions, we can compare them to their actual labels. So for sample, comma label, we're going to use random to sample the test data. Now note that this is not the test data loader. This is just test data. And we're going to set k equals to 9. And recall, if you want to have a look at test data, what do we do here? We can just go test data, which is our data set, not converted into a data loader yet. And then if we wanted to get the first 10 samples, can we do that? Only one element tensors can be converted into Python scalars. So if we get the first 0, then maybe we can go up to 10. Yeah, there we go. And what's the shape of this? Tuple has no object shape. Okay. So we need to go image label equals that. And then can we check the shape of the image? Label. Oh, because the labels are going to be integers. Wonderful. So that's not the first 10 samples, but that's just what we get if we iterate through the test data. We get an image tensor and we get an associated label. So that's what we're doing with this line here. We're just randomly sampling 9 samples. And this could be any number you want. I'm going to use 9 because this is a spoiler. For later on, we're going to create a 3x3 plot. So that just 9 is just a fun number. So get some random samples from the test data set. And then we can go test samples.append sample, and we will go test labels.append label. And then let's go down here, view the first, maybe we go first sample shape. So test samples 0.shape. And then if we get test samples 0, we're going to get a tensor of image values. And then if we wanted to plot that, can we go plt imshow cmap equals gray. And we may have to squeeze this, I believe, to remove the batch tensor. Let's see what happens. Batch dimension. There we go. Beautiful. So that's, to me, a shoe, a high heel shoe of some sort. If we get the title, plt.title, test labels. Let's see what this looks like. It's a 5, which is, of course, class names. We will index on that. Sandal. Okay, beautiful. So we have 9 random samples, 9 labels that are associated with that sample. Now let's make some predictions. So make predictions. And this is one of my favorite things to do. I can't stress it enough, is to randomly pick data samples from the test data set and predict on them and do it over and over and over again to see what the model is doing. So not only at the start of a problem, I'll just get the prediction probabilities here. We're going to call our make predictions function. So not only at the start of a problem should you become one with the data, even after you've trained a model, you'll want to further become one with the data, but this time become one with your model's predictions on the data and see what happens. So view the first 2 prediction probabilities list. So we're just using our make predictions function that we created before, passing it the model, the trained model 2, and we're passing it the data, which is the test samples, which is this list that we just created up here, which is comprised of random samples from the test data set. Wonderful. So let's go pred probs. Oh, we don't want to view them all. That's going to give us, we want 2. The prediction probabilities for a given sample. And so how do we convert prediction probabilities into labels? Because if we have a look at test labels, if we're trying to compare apples to apples, when we're evaluating our model, we can't really necessarily compare the prediction probabilities straight to the test labels. So we need to convert these prediction probabilities into prediction labels. So how can we do that? Well, we can use argmax to take whichever value here, the index, in this case this one, the index of whichever value is the highest of these prediction probabilities. So let's see that in action. Convert prediction probabilities to labels. So we'll go pred classes equals pred probs, and we'll get the arg max across the first dimension. And now let's have a look at the pred classes. Wonderful. So are they in the same format as our test labels? Yes, they are. So if you'd like to go ahead, in the next video, we're going to plot these and compare them. So we're going to write some code to create a matplotlib plotting function that's going to plot 9 different samples along with their original labels and their predicted label. So give that a shot. We've just written some code here to make some predictions on random samples. If you'd like them to be truly random, you can comment out the seed here, but I've just kept the seed at 42 so that our random.sample selects the same samples on your end and on my end. So in the next video, let's plot these. Let's now continue following the Data Explorer's motto of visualize, visualize, visualize. We have some prediction classes. We have some labels we'd like to compare them to. You can compare them visually. It looks like our model is doing pretty good, but since we're making predictions on images, let's plot those images along with the predictions. So I'm going to write some code here to plot the predictions. I'm going to create a matplotlib figure. I'm going to set the fig size to 9 and 9 because we've got 9 random samples. You could, of course, change this to however many you want. I just found that a 3x3 plot works pretty good in practice. And I'm going to set n rows. So for my matplotlib plot, I want 3 rows and I want 3 columns. And so I'm going to enumerate through the samples in test samples. And then I'm going to create a subplot for each sample. So create a subplot, because this is going to create a subplot because it's within the loop. Each time it goes through a new sample, create a subplot of n rows and cols. And the index it's going to be on is going to be I plus 1, because it can't start at 0. So we just put I plus 1 in there. What's going on here? Enumerate. Oh, excuse me. In enumerate, wonderful. So now we're going to plot the target image. We can go plot.imshow. We're going to get sample.squeeze, because we need to remove the batch dimension. And then we're going to set the CMAP is equal to gray. What's this telling me up here? Oh no, that's correct. Next, we're going to find the prediction label in text form, because we don't want it in numeric form. We could do that, but we want to look at things visually with human readable language, such as sandal for whatever class sandal is, whatever number class that is. So we're going to set the pred label equals class names, and we're going to index using the pred class's I value. So right now we're going to plot our sample, we're going to find its prediction, and now we're going to get the truth label. So we also want this in text form. And what is the truth label going to be? Well, the truth label is we're going to have to index using class names, and index on that using test labels I. So we're just matching up our indexes here. Finally, we're going to create a title for the plot. And now here's what I like to do as well. If we're getting visual, well, we might as well get really visual, right? So I think we can change the color of the title text depending if the prediction is right or wrong. So I'm going to create a title using an F string. Pred is going to be a pred label, and the truth label, we could even plot the prediction probabilities here if we wanted to. That might be an extension that you might want to try. And so here we're going to check for equality between pred and truth, and change color of title text. So what I mean by this, it's going to be a lot easier to explain if we just, if in doubt, code it out. So if the pred label equals the truth label, so they're equal, I want the plot.title to be the title text, but I want the font size, well, the font size can be the same, 10. I want the color to equal green. So green text, if prediction same as truth, and else I'm going to set the plot title to have title text font size equals 10, and the color is going to be red. So does that make sense? All we're doing is we're enumerating through our test samples that we got up here, test samples that we found randomly from the test data set. And then each time we're creating a subplot, we're plotting our image, we're finding the prediction label by indexing on the class names with our pred classes value. We're getting the truth label, and we're creating a title for the plot that compares the pred label to the truth, and we're changing the color of the title text depending if the pred label is correct or not. So let's see what happens. Did we get it right? Ooh, yes we did. Oh, I'm going to do one more thing. I want to turn off the axes just so we get more real estate. I love these kind of plots. It helps that our model got all of these predictions right. So look at this. Pred, sandal, truth, sandal, pred, trouser, truth, trouser. So that's pretty darn good, right? See how, for me, I much prefer visualizing things. Numbers on a page look good, but there's nothing quite like visualizing your machine learning model's predictions, especially when it gets it right. So how about we select some different random samples up here? We could functionize this as well to do like all of this code in one hit, but that's all right. We'll be a bit hacky for now. So this is just going to randomly sample with no seed at all. So your samples might be different to mine. 9 different samples. So this time we have an ankle boot. We'll make some predictions. We'll just step through all of this code here. And oh, there we go. It got one wrong. So all of these are correct. But this is more interesting as well, is where does your model get things wrong? So it predicted a dress, but this is a coat. Now, do you think that this could be potentially a dress? To me, I could see that as being a dress, so I kind of understand where the model's coming from in there. Let's make some more random predictions. We might do 2 more of these before we move on to the next video. Oh, all correct. We're interested in getting some wrong here. So our model seems to be too good. All correct again. Okay, one more time. If we don't get any wrong, we're going on to the next video. But this is just really, oh, there we go, 2 wrong. Beautiful. So I predicted a dress, and that's a shirt. Okay, I can kind of see where the model might have stuffed up there. It's a little bit long for a shirt for me, but I can still understand that that would be a shirt. And this is a pullover, but the truth is a coat. So maybe there's some issues with the labels. And that's probably what you'll find in a lot of data sets, especially quite large ones. Just for the sheer law of large numbers, there may be some truth labels in your data sets that you work with that are wrong. And so that's why I like to compare the model's predictions versus the truth on a bunch of random samples to go, you know what, is our model's results better or worse than they actually are? And that's what visualizing helps you do, is figure out, you know what, our model is actually, it says it's good on the accuracy, but when we visualize the predictions, it's not too good, and vice versa, right? So you can keep playing around with this, try look at some more random samples by running this again. We'll do one more for good luck, and then we'll move on to the next video. We're going to go on to another way. Oh, see, this is another example. Some labels here could be confusing. And speaking of confusing, well, that's going to be a spoiler for the next video. But do you see how the prediction is a t-shirt top, but the truth is a shirt? To me, that label is kind of overlapping. Like, I don't know, what's the difference between a t-shirt and a shirt? So that's something that you'll find as you train models, is maybe your model's going to tell you about your data as well. And so we hinted that this is going to be confused. The model is confused between t-shirt, top, and shirt. How about we plot a confusion matrix in the next video? I'll see you there. We're up to a very exciting point in evaluating our machine learning model, and that is visualizing, visualizing, visualizing. And we saw that in the previous video, our model kind of gets a little bit confused, and in fact, I would personally get confused at the difference between t-shirt/top and a shirt. So these kind of insights into our model's predictions can also give us insights into maybe some of our labels could be improved. And another way to check that is to make a confusion matrix. So let's do that. Making a confusion matrix for further prediction evaluation. Now, a confusion matrix is another one of my favorite ways of evaluating a classification model, because that's what we're doing. We're doing multi-class classification. And if you recall, if we go back to section 2 of the Learn PyTorch.io book, and then if we scroll down, we have a section here, more classification evaluation metrics. So accuracy is probably the gold standard of classification evaluation. There's precision, there's recall, there's F1 score, and there's a confusion matrix here. So how about we try to build one of those? I want to get this and copy this. So, and write down, a confusion matrix is a fantastic way of evaluating your classification models visually. Beautiful. So we're going to break this down. First of all, we need to plot a confusion matrix, we need to make predictions with our trained model on the test data set. Number 2, we're going to make a confusion matrix. And to do so, we're going to leverage torch metrics. Tricks, had to figure out how to spell metrics then. Confusion matrix. So recall that torch metrics, we've touched on this before, is a great package. Torch metrics for a whole bunch of evaluation metrics of machine learning models in PyTorch flavor. So if we find, we've got classification metrics, we've got audio, image detection. Look how, this is beautiful. A bunch of different evaluation metrics. And if we go down over here, we've got confusion matrix. So I only touched on 5 here, or 6. But if you look at torch metrics, they've got, how many is that? About 25 different classification metrics. So if you want some extra curriculum, you can read through these. But let's go to confusion matrix. And if we look at some code here, we've got torch metrics, confusion matrix. We need to pass in number of classes. We can normalize if we want. And do you notice how this is quite similar to the PyTorch documentation? Well, that's the beautiful thing about torch metrics, is that it's created with PyTorch in mind. So let's try out, if you wanted to try it out on some tester code, you could do it here, but since we've already got some of our own code, let's just bring in this. And then number 3 is to plot it. We've got another helper package here. Plot the confusion matrix using ML extend. So this is another one of my favorite helper libraries for machine learning things. It's got a lot of functionality that you can code up yourself, but you often find yourself coding it a few too many times, such as plotting a confusion matrix. So if we look up ML extend, plot confusion matrix, this is a wonderful library. I believe it was created by, Sebastian Rushka, who's a machine learning researcher and also author of a great book. There he is. Yeah, this is a side note, Machine Learning with PyTorch and Scikit-learn. I just got this book. It just got released in the start of 2022, and it's a great book. So that's a little side note for learning more about machine learning with PyTorch and Scikit-learn. So shout out to Sebastian Rushka. Thank you for this package as well. This is going to just help us plot a confusion matrix like this. So we'll have our predicted labels on the bottom and our true labels on the side here, but we can just copy this code in here. Link, sorry, and then confusion matrix, we can copy that in here. The thing is that torch metrics doesn't come with Google Colab. So if you're using Google Colab, I think ML extend does, but we need a certain version of ML extend that Google Colab doesn't yet have. So we actually need version 0.19.0. But we're going to import those in a second. Let's first make some predictions across our entire test data set. So previously, we made some predictions only on 9 random samples. So random sample, we selected 9. You could, of course, change this number to make it on more, but this was only on 9 samples. Let's write some code to make predictions across our entire test data set. So import tqdm.auto for progress bar tracking. tqdm auto. We don't need to re-import it. I believe we've already got it above, but I'm just going to do it anyway for completeness. And so we're going to make, this is step 1, above, make predictions. Make predictions with trained model. Our trained model is model 2. So let's create an empty predictions list so we can add our predictions to that. We're going to set our model into evaluation mode, and we're going to set with torch inference mode as our context manager. And then inside that, let's just build the same sort of code that we used for our testing loop, except this time we're going to append all of our predictions to a list. So we're going to iterate through the test data loader, and we can give our TQDM description. We're going to say making predictions, ... You'll see what that looks like in a minute. And here we are going to send the data and targets to target device. So XY equals X to device and Y to device. Wonderful. And we're going to do the forward pass. So we're going to create Y logit. Remember, the raw outputs of a model with a linear layer at the end are referred to as logits. And we don't need to calculate the loss, but we want to turn predictions from logits to prediction probabilities to prediction labels. So we'll set here ypred equals torch.softmax. You could actually skip the torch softmax step if you wanted to and just take the argmax of the logits, but we will just go from prediction probabilities to pred labels for completeness. So squeeze, and we're going to do it across the first dimension, or the 0th dimension, and then we'll take the argmax of that across the first dimension as well. And a little tidbit, if you take different dimensions here, you'll probably get different values, so just check the inputs and outputs of your code to make sure you're using the right dimension here. And so let's go put predictions on CPU for evaluation, because if we're going to plot anything, matplotlib will want them on the CPU. So we're going to append our predictions to ypreds, ypred.cpu. Beautiful. And because we're going to have a list of different predictions, we can use concatenate, list of predictions, into a tensor. So let's just print out ypreds, and so I can show you what it looks like. And then if we go ypred tensor, this is going to turn our list of predictions into a single tensor. And then we'll go ypred tensor, and we'll view the first 10. Let's see if this works. So making predictions, oh, would you look at that? Okay, so yeah, here's our list of predictions. A big list of tensors, right? We don't really want it like that, so if we get rid of that, and there's our progress bar. It's going through each batch in the test data loader, so there's 313 batches of 32. So if we comment out print ypreds, this line here, torch.cat ypreds, is going to turn these tensors into a single tensor, or this list of tensors into a single tensor. Concatenate. Now if we have a look, there we go, beautiful. And if we have a look at the whole thing, we're making predictions every single time here, but that's all right. They are pretty quick. There we go. One big long tensor. And then if we check length ypred tensor, there should be one prediction per test sample, 10,000. Beautiful. So now we need to install Torch Metrics, because Torch Metrics doesn't come with Google Colab at the time of recording. So let me just show you if we try to import Torch Metrics. It doesn't, it might in the future, so just keep that in mind. It might come with Google Colab because it's a pretty useful package. But let's now install, see if required packages are installed, and if not, install them. So we'll just install Torch Metrics. We'll finish off this video by trying to import. We'll set up a try and except loop. So Python is going to try import Torch Metrics and ML extend. I write it like this because you may already have Torch Metrics and ML extend if you're running this code on a local machine. But if you're running it in Google Colab, which I'm sure many of you are, we are going to try and import it anyway. And if it doesn't work, we're going to install it. So ML extend, I'm just going to check the version here because we need version for our plot confusion matrix function. This one, we need version 0.19.0 or higher. So I'm just going to write a little statement here. assert int mlextend dot version. So if this condition in the try loop is, or try block is accepted, it will skip the next step. Dot split, and I'm just going to check the first index string is greater than or equal to 19. Otherwise, I'm going to return an error saying mlextend version should be 0.19.0 or higher. And so let me just show you what this looks like. If we run this here, string and int. Did I not turn it into a string? Oh, excuse me. There we go. And I don't need that bracket on the end. There we go. So that's what I'm saying. So this is just saying, hey, the version of mlextend that you have should be 0 or should be 19 or higher, because right now Google Colab by default has 14. This may change in the future. So let's finish off this except block. If the above condition fails, which it should, we are going to pip install. So we're going to install this into Google Colab. Torch metrics, we're going to do it quietly. And we're also going to pass the U tag for update mlextend. So import torch metrics mlextend afterwards, after it's been installed and upgraded, and print. We're going to go mlextend version. We're going to go mlextend underscore version. And let's see what happens if we run this. So we should see, yeah, some installation happening here. This is going to install torch metrics. Oh, do we not have mlextend, the upgraded version? Let's have a look. We may need to restart our Google Colab instance. Ah, okay. Let's take this off. Quiet. Is this going to tell us to restart Google Colab? Well, let's restart our runtime. After you've run this cell, if you're using Google Colab, you may have to restart your runtime to reflect the fact that we have the updated version of mlextend. So I'm going to restart my runtime now. Otherwise, we won't be able to plot our confusion matrix. We need 0.19.0. And I'm going to run all of these cells. So I'm going to pause the video here, run all of the cells by clicking run all. Note, if you run into any errors, you will have to run those cells manually. And then I'm going to get back down to this cell and make sure that I have mlextend version 0.1.9. I'll see you in a few seconds. I'm back, and just a little heads up, if you restart your runtime and click run all, your Colab notebook will stop running cells if it runs into an error. So this is that error we found in a previous video where our data and model were on different devices. So to skip past that, we can just jump to the next cell and we can click run after. There we go. And it's going to run all of the cells after for us. It's going to retrain our models. Everything's going to get rerun, and then we're going to come right back down to where we were before, trying to install the updated version of mlextend. I'm going to write some more code while our code is running. Import mlextend, and then I'm going to just make sure that we've got the right version here. You may require a runtime restart, you may not. So just try to see after you've run this install of torch metrics and upgrade of mlextend. See if you can re-import mlextend, and if you have the version 0.19.0 or above, we should be able to run the code. Yeah, there we go. Wonderful. mlextend 0.19.0, and we've got mlextend version, assert, import. Beautiful. So we've got a lot of extra code here. In the next video, let's move forward with creating a confusion matrix. I just wanted to show you how to install and upgrade some packages in Google Colab if you don't have them. But now we've got predictions across our entire test data set. And we're going to be moving towards using confusion matrix function here to compare our predictions versus the target data of our test data set. So I'll see you in the next video. Let's plot a confusion matrix. Welcome back. In the last video, we wrote a bunch of code to import some extra libraries that we need for plotting a confusion matrix. This is really helpful, by the way. Google Colab comes with a lot of pre-built installed stuff, but definitely later on down the track, you're going to need to have some experience installing stuff. And this is just one way that you can do it. And we also made predictions across our entire test data set. So we've got 10,000 predictions in this tensor. And what we're going to do with the confusion matrix is confirm or compare these predictions to the target labels in our test data set. So we've done step number 1, and we've prepared ourselves for step 2 and 3 by installing Torch metrics and installing ML extend, or the later version of ML extend. So now let's go through step 2, making a confusion matrix, and step 3, plotting that confusion matrix. This is going to look so good. I love how good confusion matrices look. So because we've got Torch metrics now, we're going to import the confusion matrix class. And from ML extend, we're going to go into the plotting module and import plot confusion matrix. Recall that the documentation for both of these are within Torch metrics here and within ML extend here. Let's see what they look like. So number 2 is set up confusion matrix instance and compare predictions to targets. That's what evaluating a model is, right? Comparing our model's predictions to the target predictions. So I'm going to set up a confusion matrix under the variable conf_mat. Then I'm going to call the confusion matrix class from Torch metrics. And to set up an instance of it, I need to pass in the number of classes that we have. So because we have 10 classes, they are all contained within class names. Recall that class names is a list of all of the different classes that we're working with. So I'm just going to pass in the number of classes as the length of our class names. And then I can use that conf_mat instance, confusion matrix instance, to create a confusion matrix tensor by passing into conf_mat, which is what I've just created up here. Conf_mat, just like we do with our loss function, I'm going to pass in preds equals our y_pred tensor, which is just above y_pred tensor that we calculated all of the predictions on the test data set. There we go. That's our preds. And our target is going to be equal to test data.targets. And this is our test data dataset that we've seen before. So if we go test data and press tab, we've got a bunch of different attributes. We can get the classes. And of course, we can get the targets, which is the labels. PyTorch calls labels targets. I usually refer to them as labels, but the target is the test data target. So we want to compare our model's predictions on the test data set to our test data targets. And so let's keep going forward. We're up to step number 3 now. So this is going to create our confusion matrix tensor. Oh, let's see what that looks like actually. Conf_mat tensor. Ooh, okay. So we've got a fair bit going on here, but let's turn this into a pretty version of this. So along the bottom is going to be our predicted labels, and along the side here is going to be our true labels, but this is where the power of ML extend comes in. We're going to plot our confusion matrix. So let's create a figure and an axis. We're going to call the function plot confusion matrix that we've just imported above, and we're going to pass in our conf_mat equals our conf_mat tensor. But because we're working with matplotlib, it'll want it as numpy. So I'm just going to write here, matplotlib likes working with numpy. And we're going to pass in the class names so that we get labels for each of our rows and columns. Class names, this is just a list of our text-based class names. And then I'm going to set the fig size to my favorite hand in poker, which is 10.7. Also happens to be a good dimension for Google Colab. Oh, look at that! Oh, that is something beautiful to see. Now, a confusion matrix, the ideal confusion matrix will have all of the diagonal rows darkened with all of the values and no values here and no values here, because that means that the predicted label lines up with the true label. So in our case, we have definitely a very dark diagonal here, but let's dive into some of the highest numbers here. It looks like our model is predicting shirt when the true label is actually t-shirt/top. So that is reflective of what we saw before. Do we still have that image there? Okay, we don't have an image there, but in a previous video, we saw that when we plotted our predictions, the model predicted t-shirt/top when it was actually a shirt, and of course, vice versa. So what's another one here? It looks like our model is predicting shirt when it's actually a coat. And now this is something that you can use to visually inspect your data to see if the errors that your model is making make sense from a visual perspective. So it's getting confused by predicting pullover when the actual label is coat, predicting pullover when the actual label is shirt. So a lot of these things, clothing-wise and data-wise, may in fact look quite the same. Here's a relatively large one as well. It's predicting sneaker when it should be an ankle boot. So it's confusing two different types of shoes there. So this is just a way to further evaluate your model and start to go, maybe our labels are a little bit confusing. Could we expand them a little bit more? So keep that in mind. A confusion matrix is one of the most powerful ways to visualize your classification model predictions. And a really, really, really helpful way of creating one is to use Torch Metrics Confusion Matrix. And to plot it, you can use Plot Confusion Matrix from ML Extend. However, if you're using Google Colab for these, you may need to import them or install them. So that's a confusion matrix. If you'd like more classification metrics, you've got them here. And you've got, of course, more in Torch Metrics. So give that a look. I think in the next video, we've done a fair bit of evaluation. Where are we up to in our workflow? I believe it's time we saved and loaded our best trained model. So let's give that a go. I'll see you in the next video. In the last video, we created a beautiful confusion matrix with the power of Torch Metrics and ML Extend. But now it's time to save and load our best model, because if we evaluated it, our convolutional neural network, and go, you know what, this model's pretty good. Let's export it to a file so we can use it somewhere else. Let's see how we do that. And by the way, if we go into our Keynote, we've got Evaluate Model, Torch Metrics. We've been through this a fair few times now. We've improved through experimentation. We haven't used TensorBoard yet, but that'll be in a later video. And save and reload your trained model. So here's where we're up to. If we've gone through all these steps enough times and we're like, you know what, let's save our model so we can use it elsewhere, and we can reload it in to make sure that it's saved correctly. Let's go through with this step. We want number 11. We're going to go save and load best performing model. You may have already done this before. So if you've been through the other parts of the course, you definitely have. So if you want to give that a go, pause the video now and try it out yourself. I believe we did it in notebook number 1. We have, here we go, saving and loading a PyTorch model. You can go through this section of section number 1 on your own and see if you can do it. Otherwise, let's code it out together. So I'm going to start with importing path from pathlib, because I like to create a model directory path. So create model directory path. So my model path is going to be set equal to path, and I'm going to save it to models. This is where I want to create a file over here called models and save my models to there. Model path.mkdir for make directory. Parents, yes, I want it to make the parent directories if they don't exist. And exist okay also equals true, so if we try to create it but it's already existing, we're not going to get an error. That's fine. And next, we are going to create a model save path. Just going to add some code cells here so we have more space. Let's pass in here a model name. Going to set this equal to, since we're on section 3, I'm going to call this O3 PyTorch Computer Vision Model 2 is our best model, and I'm going to save it to PTH for PyTorch. You can also save it to .pt. I like to use PTH. And we're going to go model save path equal model path slash model name. So now if we have a look at this, we're going to have a path called model save path, but it's going to be a POSIX path in models O3 PyTorch Computer Vision model2.pth. And if we have a look over here, we should have, we have a models directory now. That's not going to have anything in it at the moment. We've got our data directory that we had before. There's fashion MNIST. This is a good way to start setting up your directories. Break them down, data, models, helper function files, etc. But let's keep going. Let's save save the model state dict. We're going to go print saving model to, just going to give us some information about what's happening. Model save path, and we can save a model by calling torch.save, and we pass in the object that we want to save using the object parameter, obj. Then we get a doc string there. We're going to go model2, we want to save the state dict. Recall that the state dict is going to be our model's what? Our model's learned parameters on the data set. So all the weights and biases and all that sort of jazz. Beautiful. So when we first created model 2, these were all random numbers. They've been, or since we trained model 2 on our training data, these have all been updated to represent the training images. And we can leverage these later on, as you've seen before, to make predictions. So I'm not going to go through all of those, but that's what we're saving. And the file path is going to be our model save path. So let's run this and see what happens. Beautiful. We're saving our model to our model directory. And now let's have a look in here. Do we have a model? Yes, we do. Beautiful. So that's how quickly we can save a model. Of course, you can customize what the name is, where you save it, etc., etc. Now, let's see what happens when we load it in. So create a new instance. Because we only saved the state dict of model 2, we need to create a new instance of our model 2, or how it was created, which was with our class fashion mnest v2. If we saved the whole model, we could just import it to a new variable, but I'll let you read back more on that, on the different ways of saving a model in here. There's also a link to the PyTorch documentation. Would highly recommend that. But let's see it in action. We need to create a new instance of our fashion mnest model v2, which is our convolutional neural network. So I'm going to set the manual seed. That way when we create a new instance, it's instantiated with the same random numbers. So we're going to set up loaded model 2 equals fashion mnest v2. And it's important here that we set it up with the same parameters as our original saved model. So fashion mnest v2. Oh, we've got a typo here. Oh, fashion mnest model v2. Wonderful. So the input shape is going to be 1 because that is the number of color channels in our test, in our images. Test image.shape. Do we still have a test image? Should be, oh, well, we've created a different one, but our image size, our image shape is 12828. Image shape for color channels, height, width. Then we create it with hidden units. We use 10 for hidden units, so we can just set that here. This is important. They just have to, otherwise, if the shapes aren't the same, what are we going to get? We're going to get a shape mismatch error. And our output shape is what? Is also going to be 10, or length of class names. If you have the class names variable instantiated, that is. So we're going to load in the saved state dict, the one that we just saved. So we can go loaded model 2 dot load state dict, and we can pass in torch.load in here, and the file that we want to load, or the file path, is model save path up here. This is why I like to just save my path variables to a variable so that I can just use them later on, instead of retyping out this all the time, which is definitely prone to errors. So we're going to send the model to the target device. Loaded model 2.to device. Beautiful. Let's see what happens here. Wonderful. So let's now evaluate the loaded model. So evaluate loaded model. The results should be very much the same as our model 2 results. So model 2 results. So this is what we're looking for. We want to make sure that our saved model saved these results pretty closely. Now I say pretty closely because you might find some discrepancies in these lower decimals here, just because of the way files get saved and something gets lost, etc., etc. So that's just to do with precision in computing. But as long as like the first few numbers are quite similar, well, then we're all gravy. So let's go torch manual seed. Remember, evaluating a model is almost as, well, is just as important as training a model. So this is what we're doing. We're making sure our model's saved correctly. before we deployed it. If we deployed it and it didn't save correctly, well, then we would get less than ideal results, wouldn't we? So model equals loaded model 2. We're going to use our same eval model function, by the way. And of course, we're going to evaluate it on the same test data set that we've been using, test data loader. And we're going to create a loss function, or just put in our loss function that we've created before. And our accuracy function is the accuracy function we've been using throughout this notebook. So now let's check out loaded model 2 results. They should be quite similar to this one. We're going to make some predictions. And then if we go down, do we have the same numbers? Yes, we do. So we have 56829, 56829, wonderful. And 31358, 31358, beautiful. It looks like our loaded model gets the same results as our previously trained model before we even saved it. And if you wanted to check if they were close, you can also use torch.isClose. Check if model results, if you wanted to check if they were close programmatically, that is, because we just looked at these visually. Check if model results are close to each other. Now we can go torch is close. We're going to pass in torch.tensor. We have to turn these values into a tensor. We're going to go model to results, and we'll compare the model loss. How about we do that? We want to make sure the loss values are the same, or very close, that is, with torch.isClose. Torch.tensor, model, or we want this one to be loaded model 2 results. Model loss. Another bracket on the end there, and we'll see how close they are. True. Wonderful. Now, if this doesn't return true, you can also adjust the tolerance levels in here. So we go atol equals, this is going to be the absolute tolerance. So if we do 1 to the -8, it's saying like, hey, we need to make sure our results are basically the same up to 8 decimal points. That's probably quite low. I would say just make sure they're at least within 2. But if you're getting discrepancies here between your saved model and your loaded model, or sorry, this model here, the original one, and your loaded model, if they are quite large, so they're like more than a few decimal points off in this column or even here, I'd go back through your code and make sure that your model is saving correctly. Make sure you've got random seeds set up. But if they're pretty close, like in terms of within 3 or 2 decimal places of each other, well then I'd say that's close enough. But you can also adjust the tolerance level here to check if your model results are close enough programmatically. Wow, we have covered a fair bit here. We've gone through this entire workflow for a computer vision problem. Let's, in the next video, I think that's enough code for this section, section 3, PyTorch computer vision. I've got some exercises and some extra curriculum lined up for you. So let's have a look at those in the next video. I'll see you there. My goodness, look how much computer vision PyTorch code we've written together. We started off right up the top. We looked at the reference notebook and the online book. We checked out computer vision libraries in PyTorch, the main one being Torch Vision. Then we got a data set, namely the Fashion MNIST data set. There are a bunch more data sets that we could have looked at. And in fact, I'd encourage you to try some out in the torchvision.datasets. Use all of the steps that we've done here to try it on another data set. We prepared our data loaders, so turned our data into batches. We built a baseline model, which is an important step in machine learning because the baseline model is usually relatively simple and it's going to serve as a baseline that you're going to try and improve upon through, just go back to the keynote, through various experiments. We then made predictions with Model 0. We evaluated it. We timed our predictions to see if running our models on the GPU was faster, and we learned that sometimes a GPU won't necessarily speed up code if it's a relatively small data set because of the overheads between copying data from CPU to GPU. We tried a model with nonlinearity and we saw that it didn't really improve upon our baseline model. But then we brought in the big guns, a convolutional neural network, replicating the CNN Explainer website, and by gosh, didn't we spend a lot of time here? I'd encourage you, as part of your extra curriculum, to go through this again and again. I still even come back to refer to it too. I've referred to it a lot making the materials for this video section and this code section. So be sure to go back and check out the CNN Explainer website for more of what's going on behind the scenes of your CNNs, but we coded one using pure PyTorch. That is amazing. We compared our model results across different experiments. We found that our convolutional neural network did the best, although it took a little bit longer to train. And we also learned that the training time values will definitely vary depending on the hardware you're using. So that's just something to keep in mind. We made and evaluated random predictions with our best model, which is an important step in visualizing your model's predictions, because you could get evaluation metrics, but until you start to actually visualize what's going on, well, in my case, that's how I best understand what my model is thinking. We saw a confusion matrix using two different libraries, Torch Metrics and ML Extend, a great way to evaluate your classification models. And we saw how to save and load the best performing model to file, and made sure that the results of our saved model weren't too different from the model that we trained within the notebook. So now it is time. I'd love for you to practice what you've gone through. This is actually really exciting now because you've gone through an end-to-end computer vision problem. I've got some exercises prepared. If you go to the learnpytorch.io website in section 03, scroll down, you can read through all of this. This is all the materials that we've just covered in pure code. There's a lot of pictures in this notebook too that are helpful to learn things, what's going on. We have some exercises here. So all of the exercises are focused on practicing the code in the sections above. We have 2 resources. We also have some extra curriculum that I've put together. If you want an in-depth understanding of what's going on behind the scenes in the convolutional neural networks, because we focused a lot on code, I'd highly recommend MIT's Introduction to Deep Computer Vision lecture. You can spend 10 minutes clicking through the different options in the PyTorch Vision library, Torch Vision. Look up most common convolutional neural networks in the Torch Vision model library. And then for a larger number of pre-trained PyTorch computer vision models, and if you get deeper into computer vision, you're probably going to run into the Torch Image Models library, otherwise known as TIM. But I'm going to leave that as extra curriculum. I'm going to just link this exercises section here. Again, it's at learnpytorch.io in the exercises section. We come down, there we go. But there is also a resource here, an exercise template notebook. So we've got 1, what are 3 areas in industry where computer vision is being currently used? Now this is in the PyTorch Deep Learning repo, extras exercises number 3. I've put out some template code here for you to fill in these different sections. So some of them are code related, some of them are just text-based, but they should all be able to be completed by referencing what we've gone through in this notebook here. And just as one more, if we go back to PyTorch Deep Learning, this will probably be updated by the time you get here. You can always find the exercises and extra curriculum by going computer vision, go to exercises and extra curriculum, or if we go into the extras file and then we go to solutions, I've now also started to add video walkthroughs of each of the solutions. So this is me going through each of the exercises myself and coding them. And so you'll get to see they're unedited videos, so they're just one long live stream. And I've done some for 02, 03, and 04, and there will be more here by the time you watch this video. But if you'd like to see how I figure out the solutions to the exercises, you can watch those videos and go through them yourself. But first and foremost, I would highly recommend trying out the exercises on your own first. And then if you get stuck, refer to the notebook here, refer to the PyTorch documentation, and finally, you can check out what I would have coded as a potential solution. So there's number 3, computer vision exercise solutions. So congratulations on going through the PyTorch computer vision section. I'll see you in the next section. We're going to look at PyTorch custom datasets, but no spoilers. I'll see you soon.